that water is projected horizontally from a point 1 meter above the ground.
Okay.
Wow. Understand? Yeah. One. Yes. The nozzle is held so that water is projected. The nozzle is held so that water is projected horizontally.
1 meter above the ground.
Yes, from a point 1 meter above the ground. Over what? Over what horizontal distance can the water be projected? Well, the nozzle is held so that the water is projected horizontally from a point 1 meter above the ground.
Yes. So, over what horizontal distance
can the water be projected? So attempt it. Attempt it. See my back. Very good. Did you get the question? Yeah? Okay, let me lay foundation for it. Read the question out.
A gardener uses a water hose to fill a 30-liter bucket.
To fill the what?
A 30-liter bucket.
So this is let's go.
It takes 1 minute to fill the bucket.
It takes he knows. Is that what they said?
It takes 1 minute to fill the bucket.
Okay.
A nozzle with air 0.5.
Hold on. So normally 1 minute fills a 30-liter bucket. Okay.
A nozzle with cross-sectional area 0.5 centimeters squared.
So area of the nozzle, that's the orifice. Equals what?
0.5 centimeters squared.
0.5 centimeters squared. Convert this one to meters quick. That would be 0.000. That would be 5 times 10 to the power of minus 4. Right? Confirm it.
Yes.
It's 5 meter square. Okay?
The nozzle is held so that the water is projected horizontally 1 meter above the ground.
So 1 meter
Height.
1 meter above the ground.
Over what horizontal distance will the water be projected?
Over what?
Over what horizontal distance will the water be projected?
So now this no longer looks like a dynamic question, it's projectile. So the initial velocity,
We don't even know.
check it.
We don't call it.
confirm what he wrote. The gardening uses a water hose to fill a. Okay. The gardener notes that it takes 1 minute to fill the bucket. He notes.
Okay, sir.
Do you understand? You understand? What's the word you understand? Look at something. He already notes that it takes 1 minute to fill the 30-liter bucket. With that, we have a volume flow rate. So that our volume flow rate can what? Can what? 30 liters over 60 seconds.
That's 0.5.
0.5 liters per second. And now that's inside liters per second. You can have meters per second. It is just meters per second dot meter square. So you can utilize it as your UES. But nevertheless, that's one of the approach. So this one now is via volume flow rates. Another good approach that you can use here is it's a hose. It has an opening, right? You can utilize your square root 2G H. Yes. Square root 2GH. That will give us actual velocity.
Well, are we using, we use 9.8, right?
I didn't hear you.
9.8.
9.8. Yes, you can.
So this 4.4, 4.43.
I work with that. Yeah. Now what? Doing horizontal motion. Are you resolving it? Doing horizontal of motion. There's nothing to resolve now. Because the initial component of velocity G is the only one that is existing at the beginning. There was no vertical component. Even the shape. So this is how your community feels. Just continue.
So now we have,
You don't have okay, we have this. I can check. What do we have? What does it mean? 0.5 divided by what? See 5 times power minus 5. Now that's you can't go to stress. Just yeah. It's giving you answer direct.
10 seconds. Or you know time in seconds, right?
Mm-hmm.
Time in seconds. I suppose 265.8 because that's the greater distance.
What do you get?
265.8.
Okay. Yes. I played. Let's do some balloon.
Look at you.
Yeah. No. Yeah. Okay. He's looking for question. Is it people too? We do lights.
Like,
We do this. You cannot.
I'm going to class up. I'm going to class up to this.
It's just the
Yes.
let me look. Let's solve questions from last night. So I have another opportunity.
Yeah. Yeah.
So
So, in what kind of question do we have to resolve into the vertical and the horizontal components?
you use this one. What's that? What's that velocity you got?
Our velocity is 1.47.
So we're having 4.43 meter per second. This one continues as ux till the end of the journey. They are not changed. You get it? But uy initially equals to what? 0. As time goes on, it can change because of gravity.
Okay. So, how the equation has come before
They want you to tell them about it. They can tell you with what velocity does it strike the floor.
Okay, like the type of velocity.
At what velocity does it strike the floor? That means you're going to be doing something like maybe strikes here, vertical component Vx, which you have to calculate, horizontal component Vx, horizontal Vx, which you already have. In every projectile motion, it is constant. But in this one here, actually have to calculate it. Utilize what? Vertical component of motion. H equals to what? Ut plus 1/2 gt squared. We are moving for this one. If it was this one, you will use plus. If it has been a normal projectile, you use minus.
So the UT have got
This is uyt. Exactly. Is it in this motion?
not in this
It's not u cos. In this motion here, it's 0.
plus UI plus 0.
Good.
Because it's not because it's from right?
So
Right.
for anything horizontal motion,
UI equals to
why
0.
0? It doesn't have any initial vertical component. So here we have this. That is why if I actually want to get the Vy, I'll tell myself Vy squared equals to Uy squared plus 2gh. If given a U and h is 1, this one is a brother to everybody. You can get this. This one is 0.
Okay.
You get to find the rest. And then just put it in and then resolve. That's that for that. Do you know Luchi? One guy, one girl on TikTok, Luchi. I used to vex every time. People laugh. They insult. Oh yeah, oh yeah, no.
Let's start so.
I like that. Oh, yeah. It said A in air, B when it is immersed in water. So what are you doing, sharp? The formula for combination of lenses is like this. 1 over focal length is equals to open bracket n1 over n2 minus 1 open bracket 1 over r2 minus 1 over r1. Because you not only pass there. But oh yeah, start.
Actually, your question is complete.
It's complete.
It's only 1 hour.
A double convex thin lens.
So if I utilize 1 hour for the look, then one.
When the lenses are identical, the sign convention states that one of them should be negative.
Now we have 1 over minus
20 minus so plus.
1 over minus 20 minus. 1 over minus 20 plus
1 all over 20 minus. You know why it is like that? You know why it's like that? So you didn't know. I just took it like that.
I've not seen this one like.
Imagine this one is a double convex, I mean.
Yes.
A double convex will be like this. That's biconvex. Right? That means this surface is the convex surface. This surface is also a convex surface, I mean. That means you can have the two convex surface pointing towards the same spatial position. One will end up, imagine it was a graph, one will be in the x-axis. Then now, imagine it was a convex and concave like this. This is what I did. Convex and concave. You understand?
Yes.
Hope you know. What are you planning to do in this place? In this place?
You're going to be the parking of transport. That's 1 over
Mm-hmm. I thought that you are going to come to the other one.
For the first one, your focal length equals to 2 centimeters.
Are you sure? Are you sure? You're sure? You're sure? Say it well.
Focal length is equals to 2 centimeters.
That's the word. Let's check.
I'm sure, sir.
MJ now.
You know, 1.5.
Minus 1.
1 over 20 plus 1 over 20.
Okay. So I have 1 by f is equals to what now?
1 over f is equals to 0.5 times
Bracket.
0.1.
2 over 20 now, that's 1 over 10.
That's 0.1. So when you multiply, f is equals to 0.1.
No, wait. When you open the bracket, what does it give you? Just take a look at you. Look at your life. But you got it, Abi? You never get it. Okay, you even said that you have not done it before. But you have learned it now. Okay. You don't tell me something. Don't tell me something. You are doing the second one exactly. This is the second one you are doing now. It's the second one you are doing now.
Yes, I'm making a negative value.
Why? Okay, focal length.
Yes.
It's time also.
In terms by sunlight and glass see data. Abi?
Yes. American. You are correct.
Thank you, sir. Let me resume.
This is one now. $18 glass.
18 gram.
Yes. Let me stress you.
Yes.
18 glass. 18 glass lengths. Open brackets. Refractive index. That's n equals to 1.50. Hi there.
Yes, sir.
I know you.
He said, how will he get to the second one?
Okay.
Yeah.
Is it clear now? This space for that one. You understand it, David? I follow us on this one.
Next question.
18 glass lengths. N equals to 1.50. I'm waiting for him. Yeah. You are sweating, brother. Just now. You not sweating before. Where's that? 18 glass lengths has a focal length of plus 10 centimeter in air.
Plus 10 centimeter in air.
Air, yes. Plus 10 centimeter in air. Right there.
Yes, sir.
Compute its focal length in water. Compute its focal length in water. Open bracket. N equals 1.33. Oh, yeah. Good. Yeah. That's what I'm telling you. You will get it if you put your mind now. I don't know you will come. When I saw it from far, I was like, Grace came.
I don't get it.
Hello, don't ever put your mind down for that kind of thing. Are you okay?
Touch my mind down now.
No. When you put your mind down, your mind will be up at the same time. So put your mind down.
And your mind is in the middle. And like not getting
You will get to think. You know that if I solve this thing, you will not be happy with yourself. I'm telling you. You will not be, you know, like, you know, you will not be happy. It's the truth. Just calm down, do it. You get it, 2 cup off. Yeah. No, wrong. Try again. You will get it. Just put your mind to it, you get it. What do you call it?
7.6.
Wrong. Try again. Now you have learned 2 ways not to do it. 2 ways. Which one? You are the way creator. Create a way. Create a way.
This one's 9.
Wrong. Try again. Why you hold your head? Do you know how many times Jesus has forgiven you all your mistakes? And he's still trying on you. Try again, Joe. Just 4. Just 4 mistakes. You have learned 4 new things if you don't know. 4 ways not to solve it. It's not something you're able to say. You will feel ashamed of yourself. Because if there was something serious in it, I won't give it to you to do. Should I solve it? Hey, child. No, Mama. After your round, are you going on? Are you going on? She should know. Let me portion and I'll cause something to cook. I just come as a you carry on the new house. Let me solve it. Since you have decided to give up on the minor thing.
I don't give up.
You
I give up
what?
on you.
Read the question out.
18 glass lengths, n is equals to 1.50.
Say you're swinging your legs. So happy that call it again, please.
18 glass lengths, n is equals to 1.50. The focal length in air is 10 centimeter. Compute the focal length in water. N is equals to
Formula. 1 over F equals to what?
And n 1 over n minus 1. 1 over r.
So we have how many focal lengths? 1.5 and 1.3. Abi? Yes. I'm not waiting again. Oh, so I just wrote and light came to you. I'm not waiting. It's gone. Gone. Now they said, have the focal length of this and of plus 10 centimeter in rear.
That's the focal length of plus 10 in air. You're finding the focal length in water.
That's the focal length of plus 10 in rear.
In air.
In air, Abi?
Yes.
Now, I will not contain myself. When this thing is alone in air, when I don't need 2 refractive index, 1 over 5. Like one we just did 1.5.
1.33.
I will not put over 1.33 minus 1. Since they give me the focal length of him alone. Get that. Get that, yeah. Get that. You see why it's paining you? Because this was enough light that you did not see.
Wait.
Reduce the black you hear. You know here.
See that she wear black.
Until you go to hell. 1 all over
R1.
minus 1 all over.
Out.
Okay, how do we intend to remove all these ones? Exactly. So you know that part.
So then I say she will blame me so bit.
I'm not waiting again.
So
No.
bit now.
You have embarrassed yourself. You have embarrassed yourself. This is how people will cry when rapture takes place. Because second chance. You have started practicing your one. Pain, you can't I feel your pain. Jesus. So from here now, what will I do? Let me just do this one divided by this one. So 1 all over divided by 1 over f equals to 1. Divide that one for me. Don't help me. No, don't help me.
Let me get the bracket for you.
For this part, don't help me.
Don't have calculator.
Bro, help me press this thing now.
You have 0.127.
I told myself. 0 point.
You have 0.127.
This one says that's 0.5.
Yes.
0.127. She not my first. You can't see that for this word now. It's F all over 10.
3.9, sir.
Final answer.
No, that value, that was 3.
Sorry for you.
That's 10 times.
Who is passing through that way? You think I'm passing? I'm following to pass that long court. We'll meet in the house. See you. I don't reach house.
The answer is 39.3 centimeter.
Something you would have gotten and be proud of your life.
I'm ashamed of myself.
You don't need to tell me. Yeah, I know. Where you want to help?
Next question. Next question.
What do you best and enter question?
Next question, sir.
And also finish for today. Right? And I know it's good. Oh yeah.
Next question, sir.
The questions.
Yes.
Before you leave anything international academy, you're going to write a summary of everything you know. That's what I use and give you your certificate. You know, without certificate, you can use the results.
Sir.
You can start writing it. Don't worry. Just summarize. Don't make it too brief. At least 3,000 pages.
Sir, you don't go 3,000 pages.
That's why I said you do 3,000.
Write 3,000, they're going to write 5,000.
Oh yeah. Compute. No, wait. Right. What must be the focal length of a third thin lens?
A
Third thin lens. I choose only 3.
Don't tell us the beginning.
What must be the focal length of the third thin lens? Placed in close contact with 2 thin lenses. With 2 thin lenses of 16 centimeter and minus 23 centimeter. Is that not blessing? Okay.
Of 16 centimeter.
16 centimeter and minus 23 centimeter. Angel, how are you? Since time you're just coming.
Sir, continue.
Oh yeah, now 16 centimeter minus 23 centimeter focal length.
And
To produce a lens with minus 12 centimeter focal length.
sir. And
What? You're not playing. So, what must be the focal length of the third thin lens? Placed in close contact with 2 thin lenses of 16 and minus 23 centimeter focal length to produce
be the focal length of a third thin length placed in contact with two thin lengths of 16 centimeters. That's R1
Yeah?
That's R1 Yeah?
Whatever you think. And you want me to help you again?
No.
That's the spirit. Huh? 19. 19 by what? Wrong. Wrong. Just do again. Try again. Wrong. Wrong. Try again. Think. Ridiculously unique. Okay, the answer. You see, when you have so many problems, you know the first thing you should tell yourself, the solution exists somewhere. So, what's going on there? I've not finished with me. Let me show me myself. Oh, yeah. Have you gotten the answer? Have you gotten the answer? Why have you guys not gotten the answer? We are thinking when we are not giving us in beside me so we Latin like that. We are thinking one way. Because this is the formula on the board, what makes you think that this is what we use? Read the question out.
What must be the focal length
Yes.
of a third thin length?
What must be the focal length of a third thin length? Meaning we have how many lenses available on ground? 3. Right? Good.
Placed in contact with two thin lengths of 16 centimeter and minus 23 centimeter.
In what? In focal length?
Produce a focal length of minus 10 centimeter.
Now stop. So they are trying to let you understand that there are a total of 3 lenses.
Yeah.
They gave you the value of 2 lenses focal length.
Mm-hmm.
They now give you the combined focal length of all the 3. And I'm sure you know that normally the combined focal length of any combination is usually equals to the sum of each of the other.
Yes.
You know this thing, Abi?
Yeah.
So what are you doing since? So don't take over for what I've started though. I don't lay foundation for people. 1 all over 10 is equals to what? Okay, it's the summation minus 1 over 10.
Yes.
Minus 1 over 10 equals to 1 all over focal length of one of them. 16, Abi?
Yes.
Plus, is it plus minus? Minus 1 over 23. Still your face now, you're not happy with yourself. Something you just do and get. I take it one way. So what do we have from here now? CF3 smiling, looking at somebody. I have 1 over F3 equals to 1 over 23 minus 1 over 10 minus 1 over 16. LCM. LCM. Have you don't know how to do LCM? Oh yeah, LCM fast. Oh yeah, that's it now, multiplying everything. 3,000. Oh yeah, this one divided by, it will give me 160. Minus, this one divided by this one. It give us what? 368. Oh yeah, 230. 230. 230. 1 over F3. Do the numerator.
Minus 438.
Yeah. I know you.
Minus 8.6 centimeter.
It's enough shame for the day. Just scream, don't worry. So, that's that for that one. That's that for that one. Okay, the toilet, I thought it's another one. So that's the case. Should you solve one more? What if this one more makes you feel down? I beg you, leave am. So we are done with this night is when we treat the other things.
We're done with optical.
Yeah.
What are you going to do?
Yes, atomic physics.
Atomic structure.
Yeah, atomic structure, yeah. You're coming back now. So, okay. Yeah? No, we didn't use this one. Actually, they are rotating in a very short time. They are rotating now. They are rotating now. The audience. It's not now. Boss. Anna. Let's just pick one. Let's solve one. Let's solve one. Now, as shown in the diagram below, an object is placed. As shown in the diagram below, an object is placed 40 centimeters in front of a converging lens. As shown in the diagram below, an object is placed 40 centimeters in front of a converging lens. That has F equals to F equals to plus 8.0 centimeter. A plane mirror is 30 centimeters beyond the lens. Find the positions of all images formed by this system. That's about to draw. Alright, so is that interesting? Well, these are important. Okay. Okay, so too. So that's for that. So um you can do it at home. Eh? No problem, I want to use myself. Well, thanks a lot for the awareness.
Sorry?
we are about to commence one of the most important aspects of physics, atomic structure. It goes beyond the name. It's so when we hear the word atomic structure, we are talking about the structure of the atom. Now, just to give you a clear view of what we're about to do. The structure of the atom runs from what people perceive it to be before advancement in physics to what we appreciate it to be now. Then we are going to be looking at the limitations why we couldn't stay with the previous postulations, why we had to modify the postulations, and the present problems we're having with the recent postulations. We're going to be exploring all of it. Then we will now lay a good foundation for energy quantization, because that foundation happens under this topic. This is the first topic in modern physics. I get it now. It's the first topic in modern physics. And when you hear the first topic in modern physics, that's like we're saying it is not even a part of classical physics. Classical physics is all your mechanics, your motion, your heat, your waves. It's the first thing through physics. So if you're going to understand all those things that happened with Heisenberg and Albert Einstein, this is where it happened. So we're going to start very easy. The atom. The atom. I believe you've heard of atom before. You've heard of the atom before. You've heard of it. Very good. So many controversy about the atom. Some say it is the smallest divisible. Some say it is divisible. All those plenty things. I'm going to tell you and show you how you're supposed to think of the atom. Now let's start by saying the atom, right, is the smallest and basic unit of any element. Whether it is divisible or indivisible is not even the point of importance. That's the funniest part. The truth is, the atom is made up of different parts. And because of the fact that it's made up of different parts, that's why people say it is divisible. I guess what I'm saying. So we are at that point now where we know that, okay, the atom is the basic, smallest, functional component. I'm not making mistakes. I know that to some people it looks like cell. No, I'll explain this definition to you now. When you check advanced books, you see that this is what they utilize. This smallest functional components of all elements. Functional in the sense that the parts that makes up the atom, every single one of them play a role to the functionality of the atom. The nucleus enable in taking part in nuclear reaction and keeping the identity of the element. Also control stability of the element. The electron responsible for chemical reactions. Orbitals are responsible for what? For holding back electrons and establishing electrostatic balance. Everything has functions. Every single one of them have functions. So I want you to note this down. Now, when you've noted this down, we're going to say the atom is divided into. Atom is divided into how many parts? 2 parts. Thank you. What are 2 parts? We have the nucleus and the electrons. Are you getting me now? Try it. The nucleus and the electrons. Atom is divided into neutron. The nucleus, not neutron, the nucleus and the electron. So I'm saying that this is the atom divided like this. We have the nucleus part, we have the electron part. I guess what I'm saying now. These nucleus parts, what do we have in these ones? Two things. We have the proton and we have the what? Neutron. These electrons, how many types? We have two classes of electrons. We have the valence electrons. And what do we have again? We have the core electrons. We have the valence electrons and the core electrons. In nucleus, we have the proton and we have the neutron. You see that now? We have the proton and the neutron. Electrons, we have valence electron and core electrons. When you hear the word core electrons, what are we saying? The core electrons are the inner electrons. Inner electrons. And guess what these people do? Their presence results in what we call screening effect or shielding effect. Let me become a bit graphical. This is the nucleus. 1, 2. You start seeing electrons around, Abby. Start seeing electrons around. Now, this is the powerhouse of the atom, the nucleus. Because it's from the nucleus that the nuclear force that keeps all electrons stable in check in their orbital. It's from there it emanates. Now, tell me, what do you think the presence of these particular electrons in this shell and this shell are doing that affects this guy? They are blocking, let me use the word obstruct. They are obstructing the free access of this electron to receive nuclear energy, right? Now, that process is what we call screening. And some people call it shielding. So I'm saying the more inner electrons, the more the shielding effects. Do you see that now? The more inner electron, the more shielding effects. So that's the inner electrons, and they are responsible for shielding. Responsible for shielding. Valence electrons. These ones here are the ones responsible for determining the oxidation state of elements. Determining the oxidation state of elements. Now, whether you are a core electron or you are a valence electron, in as much as you are an electron, what charge do you bear? You are a negatively charged body. You are a negatively charged body. All electrons are negatively charged. But when you come to the nucleus, the proton is the positively charged subatomic particle. The neutron has no charge. So therefore, if only these two things make up the nucleus, what do you think will now be the charge of the nucleus? Since the nucleus only contains something that is positive and no charge, automatically the nucleus will have what charge? No, it will have positive charge. You know, if inside this circle, I only have positive balls and some other particles that are no charge, altogether, what will be the effect charge that I will carry? Positive. Because these ones are just neutral, they're not doing anything. Just take note of that. Take note of that. All right. So, the protons are positively charged. This one, no charge. Okay. Now, there are different models that exist when it comes to atomic structure. The first and most important model we're talking about is the J.J. Thomson model. We call it the plum pudding model. Have you seen a plum pudding before? It's a plum pudding. Designer plum pudding, you have resins, all those maybe pepper, all those varieties. It look like corn pudding. But you've not seen any pudding before. You've not seen any pudding before, any type of pudding. The food is so okay. So when you open the pudding, you see things inside, like a lot. So that was what J.J. Thomson compared the atom to. We call it plum pudding model. So let's start talking about the contributions. Contributions to atomic structures. Contribution to atomic structure. Yes. How is it? Ready? Okay. Now, the first person, J.J. Thomson. J.J. Thomson. J.J. Thomson, even before that was somebody called John Towson that contributed to atomic theory, and he put forward a structural model called the billiard ball model. But that billiard ball model was not, was not scientifically enough to be accepted by the actual science. It had a lot of limitations. It could not explain so many expected properties of the atom as a day. So they laid that model. The first a big reasoning model that was even adopted was that of J.J. Thomson. So J.J. Thomson's model was called the plum pudding. We call it the plum pudding model. Plum pudding. Plum pudding model. In the plum pudding model, in case they ask you in theoretical development level or any student, in case they ask you in any exam, and it is a theoretical exam, they ask you to describe the plum pudding model, you can easily understand that J.J. Thomson saw the atom. He described the atom as a positively spherical charged ball. As a positively spherical charged ball with a negatively charged electron, which he described
as the result, and I'll put it in the bracket for you. Negatively charged electrons embedded within them. So structurally, this was what a velocity atom looks like this. Positive, 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 positive. Yes. So this was how he described the atom. This sphere, I believe, was positive sphere with negative electron. So this would not account the presence of protons and nucleus. So that it could not also account. These are limitations to this model. Could not account for the stability. Now we have to look at stability, nuclear stability and the general atomic stability. It could not account for the atomic stability of the atom. Those limitations were really not for them to discard the model. But J.J. Thomson was probably a very legitimate scientist because while he was demonstrating and describing the model, he was carrying out work to find out what these negative charges were. He wanted to understand the properties of the negative charge. And what did he do? He designed something. He was one that designed the cathode ray tube. Cathode ray tube, also known as the discharge tube. Some people call it Planck's tube. Whatever they don't bring it to you in the exam, just remember. Now, okay, how did this begin? So it all started from this glass tube. This particular glass tube was a special glass tube. It had an opening here that we called a vacuum pump. Some people call it a vacuum, an air evaporator. Or pressure regulator. We had it. This glass tube, he treated the glass tube with something called zinc sulfide. I following. The man had the glass tube. He treated the glass tube with zinc sulfide. What is zinc sulfide for? Because he was about to play with radiations. He was about to play with something the human eye can't see. You don't know it is there. Example of something that is dangerous you don't know is there is electricity. Do you see electricity? It's until you touch it, you repeat it. Right? And sometimes people don't need to repeat it another time. First pay might be the last pay. So, like that, it just knew that there had to be a way they could have evidence to show that radiations were either produced during the experimentations or not. Now, within the tube, there were electrodes. These electrodes were connected to a power source. They were connected to a power source. This power source was a battery and had at least a minimum of 20 kV. This, okay, I understand that you know that this is how they do the battery. This varies. Need to see, you need to see. Okay, so basically, when you have like this is the right way of doing battery. You understand? Because a battery is like, one is like a collection of cells. Do you get it now? And you collect numerous number of cells. So this is the way we use to indicate it. But in contemporary science, once we put that symbol, we are not telling you it's a cell, but we are telling you the power source. You understand? Just telling the power source. There are specific ways you can designate to specify, the power source I'm talking about the battery, the power source I'm talking about is the cell, or is the lead acid accumulator. There are different ways to use it. But for general, we use the simple. So 12,000 kilovolts. Now, we have that in there. This zinc sulfide treated glass was to allow fluorescence. What's fluorescence? Whenever a radiation strikes on the regions that are rubbed or treated with the zinc sulfide, that region will glow. So that's the only way you use and something happened there. You know what I'm saying? The evidence and proof of events must either range from organoleptic tests or visual evidence. Organoleptic in the sense whether it's about you tasted it or you smelled it or you understand. If not, you're giving us something visual, of which you had something visual, because every single time those invisible radiations were propagated, he saw them with either fluorescent evidence or scintillation sparks. That's how scientists treat these things. But we'll get there. Now, come back here. Now, to set this discharge tube into working conditions, we need high voltage of approximately 20 kilovolts, which is 20,000 volts. And we also need a low pressure. We also need a low pressure. Low pressure. Okay? Now that we have this, Chief, there's no technical team on board. I'm more concerned about this timer. Okay. So yeah, when I mean putting all these things into functional working conditions, I'm talking about him being able to set up a high volt system of 20 kilovolts through these power sources that we designated here and remove evacuate gases from the discharge tube either to prevent ionization and all. So what happened is this, was to set this into play, he observed that certain radiations were traveling from this electrode. Now let me tell you something, this electrode is connected to this, hope you know that this is the negative terminal and this positive terminal. How do you know the negative terminal is one smaller? So if I connect the smaller side to this electrode, it means it's the negative electrode. It's not positive, they don't do negative. This one is a continuum setup. So if this is negative terminal and I want to make another one negative, I need to just connect it directly to the negative terminal. So this becomes the cathode. Becomes what? Why does that becomes what? Anode. So during the experiment, he found out that radiations were coming out from the cathode and they were traveling in an organized manner straight up to the anode, as if the anode was their target. So it gave a reason to study those radiations even more. He needed to know what those things were. What did they not do? Because someone can feel that it's a coincidence and this is just like maybe they just like traveling straight. So what did he do? He now created a deviational setup of an electric field that allows intentional deviations. I get it now. That's only subject to what? That's only subject to polarity. Polarity based on charge. Now look at what I'm talking about. Around the pole, around the surface here, he had another electrode. Down here, another electrode. This one was the positive electrode. This one was the negative electrode. Then he repeated the experimentation to see if these things will still continue traveling here straight. But guess what? When he set up this something, what did I do next? What did I do next? What does it do? What did I do next? What should we do? So what did he do next? He now set up something and found out that this thing that came out and traveled straight before did not come out and travel straight again. They deflected to the positive electrode. If you were the one, what will be your conclusion? You know that this is positive electrode and all the radiations bent to the positive electrode. Based on polarity, it becomes a conclusion in your head that these radiations are negatively charged. Because we know that negatively charged particles will always want to get deflected to where positive electrode. Troubles. So that was its first inference. I get it now. So if you want to write in the report, you will say it's subjected the discharge to what? To electrostatic fields. And what was his observation? He found that what the radiations deflected to the where? To the positive electrode. What is the conclusion? This shows that what the unknown particles were electronegative. They were negatively charged. Just what you say. That's it. So you can write it down. Make your report. We have that. So you can write it down. Just write what I'm going to say. You can leave space for the diagram, you complete it later. All right. J.J. Thompson subjected the discharge tube. He subjected the discharge tube to an electrical field. He subjected the discharge tube to an electrical field. And then, where he later observed that the vibrations reflected to the positive electrode. Reflected to the positive electrode. And then now, which later served to be which later served to be the first obtained characteristics of the electrons. The first obtained characteristics of the electrons. The first obtained characteristics of the electrons, which is what? What's that characteristics? They are negatively charged. First obtained characteristics of the electron, that is, they are negatively charged. Negatively charged. Are you with me? Okay. So now, having done this first experimentation with the same discharge tube, he now subjected the discharge tube again to a different thing. What was that thing? Magnetic field. The fourth experimental thing is G. And so it's subjected to a what? Magnetic field. So he placed the magnet here. And here it was a horseshoe magnet. All those ones that can wrap around it, like horseshoe magnet, can wrap around it. So this was like the North Pole, it was like the South Pole. Now, I want to ask you guys a question. If there is a magnet on the wall, and I'm walking, and this magnet deflects me, like it moves me fast, quickly, with force. I get now. It gives one equation about me. Aside from the fact that maybe I'm iron, it means that I am very light. Because somebody who is a bit more a heavier person, it might deflect the person, but not easily. The angle of deflection might be small. But when it deflected the electron, the angle of deflection was high, meaning that the electrons were lightweight. That's why they mean that electrons have the smallest weight in the atom. We will use the word negligible mass. So you have this one here. Here you see is then subjected. It then subjected the discharge tube. The discharge tube. It then subjected the discharge tube to a magnetic field. To a magnetic field where it observed where he observed a high level deflection. Observe a high level deflection. A high level deflection. How would you get that? You observe the high level deflection. And that made him come to a conclusion which drew another light about the extreme low masses of electrons. That is, they have negligible masses. Yes. No. Yes. So he had to treat the glass with zinc sulfide so that when those electrons make contact with the glass, it will fluoresce to create light. That's a good question. So, the next thing now is that he subjected the field to an obstacle. An obstacle. He placed an obstacle. And what did he observe? He observed that what? That when these radiations were traveling and they struck the obstacles, all the regions towards the cathode, because these are the cathodic region, they glowed up. While these regions here, they darkened. Proof of what? Proof that these radiations can only exhibit rectilinear propagation. And then prove that they could only exhibit rectilinear propagation. That means they could travel in straight lines. You feel me? They could travel in straight lines. Now, because if these things could bend, they would have found space and then have come and brighten this place. So why was this place dark? Because the shadow of this person was casted on this place. That had to prove that something moves in a straight line. As I'm standing here, the reason why you are seeing my shadows here is because that light is traveling to me and it cannot bend around me, if not, it would have bent. It only travel in a straight line, strike me, and by striking me, my shadow will cast. And that's what happened here. Strike, it could not, this place glowed up, and that made the shadow of this one cast on this region and caused the darkened result that we saw. Like this middle here. This place is blocked. This place is blocked, don't worry. That's what you're thinking. Now you're thinking that the light will pass there and glow up. Oh yeah. So the obstacle, that is That was the case number 3. Case number 1 was the what? Electrical field. Case number 2 was what? Magnetic field. Case number 3 was what? The obstacle. The obstacle. So in the obstacle, he placed an obstacle along the path of propagation. He placed an obstacle along the path of propagation. I get it now? Along the path of propagation. Stop. When the light incident on the obstacle, the cathodic regions glued up. Cathodic regions glued up. The cathodic region glued up, and the region to the anode darkened due to shadows cast by obstacle. Cast by obstacle. Rolled up, and the region to the anode darkened due to shadows cast by obstacles. Full stop. Then obstacle. Full stop. Okay, so this proved that the unknown cathode radiations were what? Traveled in straight line. Traveled in straight lines. Yes. You know, as I then, you know that it was cathode ray. I just had prominent for you so that when you are reading, you know that the name of the rays are cathode rays, which are made up of electrons. You know, it was the electrons we were trying to discover. So it is the one, it was J.D. Thomson that discovered electrons. But there were so many other things about electrons they tried to find out, but he could not. There were so many other things they tried to find out, but he could not. All right, so that's that for that. Then, yes. The high voltage of. Okay, it's this side.
The contributions we are talking to, what are these? And it says with the negative charge electron. Then you have to bracket.
Okay, resonance. Oh, resonance are like particles. They are like particles that they find in. It's just like ingredients. You know, if you cook something or more, you do know when you see pepper in some places now. Those are resins. the extra things. The extra things you put in, the extra things you put in ice cream is not what goes. And that one is it. So that was how he was able to know that these radiations exhibited rectilinear propagation. They could not bend. They caused anodic darkness due to the casting of shadows by the incidence of cathode rays on an obstacle along the axis of propagation. It's simple as that. Now, the last thing they did was to place a rotor. You know a rotor, Abi? When you open DVD, that's the rotor. I tell you, that's the rotor. That's the rotates. When you open fan, the thing rotating. That's rotating there. They put that thing on. That thing has to drop. I will try my best. You know that thing has opening at the middle. Try. So they play a rotor along the axis of propagation. He remove the obstacle. This is a rotor. Remove all this. You understand now? So imagine this one no more there. They found out that when this thing went and strike the rotor started rotating. Chineke. Not connected to nothing. Just the same way, see something. As I push this much, you move that. But are we connected? The job I matter is that the proof that I have energy in me is that I can induce it into you by contact. I get what I'm saying now. So, for the fact that the rotor could gain kinetic energy from the collision between himself and the radiations, it proved that those radiations had energy. They had momentum that they could induce. That's the proof that they had mass. Even if the mass was small, almost negligible, it was there because it could cause the rotor to rotate. Why does it look like you are pushing for J.J. Thompson? The man is long gone. He's long gone. It's only his sons who can do it. Great grandsons. You still find out. Think all these things. They were not scrolling on TikTok now. Let's move. So, it then finally he placed a rotor along the axis of rotation along just observing the fan for 1 or 2 seconds. Along, when something starts abnormally, you have to observe. See your paper. Thank God I was still observing. Finally, he placed the rotor along the axis of rotation and observed that the rotor began in my neck rotating. The rotor began rotating. The rotor began rotating. Full stop. What I said is improved. It proved that the electrons, which we could see as radiations, had kinetic energy / what we call mass. But we know that it takes somebody who has mass to have energy. It takes somebody who has energy to induce energy. Are you there now? Okay, now this was J.J. Thomson's work. We now take steps to the next scientist, which is who? Rutherford. After J.J. Thomson's work, the next person's work was Rutherford. Ernest Rutherford. Sorry. Please don't write Rutherford. We have to go chronologically. Let's move in chronology. The next person after him was the man who came to come and do oil drop, named Robert Millikan. Robert Millikan. Now, who discovered the electron, everybody? J.J. Thomson. Exams like JAM, exams like JUPEP, they are not for see. They know that Nigerian students like to pick answers by assumption. It's why they know. So because you know that J.J. Thomson was the one that discovered the electron. If they ask you in an exam who discovered the charge of an electron, you go rush feed J.J. Thomson. And come out and the answer was your exam. You will tell them at the black from your prayer was God answers your prayers. You don't know that the host of heaven was laughing at you. They were laughing at you. Why? Because yes, J.J. Thomson discovered the electron, but he could not obtain the charge. What do I mean? He didn't know that the electron had a charge of 1.6 times 10 to the power of minus 19 coulomb. He did not know. It was this man, Robert Millikan, that came and performed an oil drop experiment that was able to establish that fact. Do you see it? But yes, J.J. Thomson tried. He got a number. That number, we call it the charge to mass ratio. It's called, everywhere is good at it. The fact that I relax, I'm relaxed. So, J.J. said something important. No. So yes, J.J. Thomson tried. He got a number that we call the charge to mass ratio. If they ask you who discovered the charge to mass ratio of an electron, the answer is who? J.J. Thomson. But who discovered the charge of an electron? Who discovered the electron? J.J. Thomson. Who discovered the charge of an electron? Robert Millikan. Mass to charge ratio? J.J. Thomson. Do you understand? There is no twisting. They want to twist it and come and make you go and pick English. You will know you have heard it before. Sharp. Even in like 100 level, they always those ones that's their lifestyle and pattern. To make sure that they bring misconceptual things to shame people. All right, let's move on. Robert Millikan. The name of his experiment was the oil drop experiment. The oil drop experiment. The oil drop experiment. Now, what was happening in this oil drop experiment? If you can pay attention, you will like it. Believe me. Now watch. Robert Millikan built his personal experimental setup like this. Alright. Test the microphone 1, 2. Okay. So, you see chamber. You see chamber. From this side, there was an opening to release X-ray. For the release of X-ray. From this side, there was an opening to observe the events that were going on inside this place. Drop your eyes here. Your eyes. So, I smile like my drawing. Now, in this side here, you open it, there was an atomizer in this place. Atomizer in that time look like this, it will be pumped. Now, the squeezing is, it will now spray this hot oil inside this place in droplets. But this chamber has a tiny opening here that we call an orifice. Yes. That we call an orifice. You see, it's through this hole that material that is getting sprayed inside can enter and be dropping small droplets. So how many chambers were clinical oil drop experiment? 2. Chamber 1, where the oil is being sprayed, and what again? Chamber 2, where the X-rays will be released. Don't worry, it's a story. A very interesting story. Now, that stories you need to learn to tell your children in bedtime. Bedtime stories. Why now? You're not giving me the mindset of your mom takes out to forget that when you just sleep before she go back. So look at this now. Now look at it. This is the water oil. This is the atomizer to spray it in tiny droplets. Now, when he connected this thing to a power supply, Good. Look at this set of everybody. You are learning. What I tell you about the longer line? The longer line and the positive value. What is the smaller line and the what? Negative. So if the negative connected to this plate, that means this plate will be what? Negatively charged. So this is the negatively charged plate. While the up one was connected to the positive, that means this is the positively charged plate. That means it's as well as calling this one your anode, positive charge plate, and this one is always cathode, negative charge plate. Sorry. So, Let's go. So, spray the oil. Obviously, follow me. As they spray the oil there, you know, some of the oil will enter inside this hole. And what will they do? They will just be dropping, I mean, till they finally drop to the ground level, two of us. That's the normal thing that would have happened. You see where physics at work. The moment they connected this thing to this power source, obviously, before they on this power source, when the power source they not connected it, what was making the oil drop? What force? Gravitational force. Is that not true? It was only gravitational force. So gravitational force was not making it fall. But when they on this thing, this place now is positively charged. Why this place is what? Negatively charged. And we know positively charged things, they like attracting negative particles. Now see what will happen in this place. When they on it and they spray this thing again, second time, as the drop of oil were coming close, they went to go and on the X-ray machine. And X-ray, they don't want to choose. The X-ray started coming out in straight lines, There's a protector glass that they don't enter their eye. Straight line. So obviously, what do you expect? As the oils were dropping, it will look as if shower of X-ray bath them first. And what that thing causes is that it makes them electronegative. It makes them what? Electronegative. So that means this oil that was here, the moment they come in contact with X-ray, the moment the X-ray collides with them, are you following me? The moment the X-ray collides with them, what happens? They become what? The oil become more electronegative. Troubles. My question for you is now this. So, this oil now that is now electronegative, be sincere, the oil is no more neutral again. It's now negatively charged. Do you think the oil will just fall down normal? Oh, what's your name? It's because I don't come on my wallet. Don't worry. Don't worry. As I came on my wallet, they will do what? What is repelling them? The fact that it's on the negatively charged, it will push it up. And as they want to push it up, gravity is still also trying to push it down. What do you think will happen? There will be a point in time where they will not find themselves, the oil will find itself suspended. It cannot go down, it cannot go up. What happened at that point? It cannot go up and it cannot go down. What has happened? What happened? Think. What do you call it? This boy deserves a scholarship. See that guy that is using that phone there? That guy that is using that phone there. After this, go and meet him down there. See something. And that's the truth. Equilibrium of force. The fact you can think it means that you have it. Equilibrium, simple. In fact, aside from the fact that repulsion is pushing this oil up, the plate up is the positive plate. It will be trying to attract it too. So, this is the oil. Gravity force acting down. Electrostatic force pushing it up until they attain equilibrium is the point now here for this setup where the Fe is equal to the what? Fg. It was through this that this man was able to get the charge of who? of an electron. They will not believe me. But see, this person was my student. He said to me, yes, bro. That's about 2,000 years ago now. 2,000 years ago. But I don't know. Who's doing all these wonderful things? My own is finer than this one. Pick between my own and this. What's finer than this one? This, where is the X-ray? Somebody asked, where is the X-ray? This person X-ray. The X-ray has broken. That, okay, you can see his atomizer, I can see his hot oil, I can see the eyepiece, but where's the X-ray? It needs to be banned. You need X-ray to release X-ray that will collide with the oil. But this is the final version. You can see the source of X-ray here. You can see the atomizer. This one is final, not like this. Cool. See it. Where is the power source? Where is the power source? Simple power source. Where is this specific power source? But then they draw. See the orifice. Every single the orifice. Where the oil will drop through, X-ray collide with it. Before you know it, more shoutings. So let's come back here. You know what? They used oil. So a brief write-up. Millikan utilized oil drops to test for the charge of an electron. So he was able to obtain the charge of an electron through the equation of equilibrium that existed this oil drop experiment.
Why is it that it's only oil that's used? Why do you see that?
Because oil is neutral. Oil is not negative. Oil is not positive. You understand? Neutral. You are the one that induce charge to it by knocking off the positive charge and making it become. That's why the actually if we use a charged particle, people will say the experiment was a biased experiment. So you have to make sure that the experimental setup, you always have to have a true experiment or we run our experiment making use of inert substances. And what are the opportunities? Go and check it. In fact, these are the calculated, this is what everybody see. This was how got that equilibrium that existed between gravity and what we call the static force led them to derive to this extent. Remember I told you that Jesus obtain charge to mass ratio. See the charge to mass ratio. Charge to mass ratio. So say Jesus and quoting the charge to mass ratio. He just put it and made mass, put the value of the mass of the oil. Then he made so the formula you could not get Q. This is mathematics. And guys, the same way I take teach Millikan, the same way I take teach. It's just now. So that's it. So if you also want to start. So that's it. So everything is all right. Okay. Now we are good. Up and running. Up and running. Up. Running. So tell the AI when you copy this down and say I can fit one. You have tried it, have you? So yeah. After Betica, the next person that came on board was Rutherford. This is good foil experiment, also known as alpha scattering experiment. Any of the two names is okay. Any of the two names is okay. Alpha scattering. Let them bring out the diagram. It's good for an experiment diagram. Don't fit. So, Rutherford was the one that discovered proton. He discovered the proton. It's fine. Çok fazla şey. He forgot to put the AI forgot to put play polarizer. So yes, this was the good foil experiment. These good foil experiments occurred such that we had an aluminium foil like this. It's just like a screen that was treated. It was treated with lead sulfide. With what? What do we use to treat the cathode ray? Zinc sulfide to allow fluorescence. But this one lead sulfide to allow scintillation. To allow scintillation. Now, the question now is this. If I ask you a question, in the atom, what occupies the greatest proportion inside the atom? Maybe we say nucleus, maybe we say proton, but the answer is empty spaces. Because if I draw an atom for you now, this is what it looks like. Nucleus, you see. If you look at all these places there that there's nothing there, all these places that are empty space. So it now looks like the atom has more empty space than things. I get what I'm saying now. It looks like the atom has more empty space than things. So the point is, this gold block is also made up of atoms. And he believed that if you fired alpha radiation, this alpha radiation, they were coming out earlier before, they were coming out rotating anyhow. But this plane polarizer, it only allowed those that could polarize in this plane to pass through. So, he found out that when they incident the gold block, some of the radiations passed through at scattered angles. At scattered angles. Some of them bounced back at scattered angles. While some bounced back undeflected. The question was ourselves with this. Those radiations are able to pass through. What must have made them pass through? Because they utilize the empty spaces in the atom. Because the gold block are made up of atom. We might not see the space, but they are there. So the radiations that pass through radiations passed through some. Radiation passed through due to due to some radiations pass through due to empty spaces. Due to empty spaces within the gold block. Due to empty spaces within the gold block. Yes. Why those that deflected back? Those that deflected back did so due to repulsion upon approach with like charge, which he called protons. Yes. Rutherford also had his model. He believed that the nucleus is centrally placed just the way we have in the sun, with electrons orbiting about it. Electrons orbiting around them. That was what he believed. So his own is, he saw the atom as having a central dense nucleus that is positively charged with electrons orbiting around it. But yes, he also had limitations. Could not describe the quantum properties of orbitals. Limitations could not account for quantum properties of radiation. Also, it could not explain nuclear stability. Could not explain nuclear stability. Yes. After this man Rutherford, the next scientist that came on board is Niels Bohr, a student of this. The name of this man's model is called planetary model. I forgot to mention this model I drew. The name of this model. You know, this was the experiment to prove that atoms had empty spaces and they had positive charges. But this one is the model. We believe the atom look like this. And the name of this model is called planetary model. His student Bohr was the one that now worked in terms of quantization, was able to explain orbital theories. You understand? But eventually, the student also was not, they still found one thing. They still found one thing. It does not explain the quantum mechanics of orbitals, of orbital clouds. And then Schrödinger is the man on board at the moment. I'm still waiting for him. You know, some of these physicists, they spend their entire life committed to only one achievement. Tell you, some of them started pursuing those dreams as early as age 12, and they were focused on it till 80. Everything about their life was not normal. Marriage, you know. School, some of them don't go to school, some of them will not keep friends. But they always in their reading room. It's a good thing, but just try to show you that anything you want to pursue, God's knocking. You don't want to know this business. Stay locked where it is. You're solving questions. The same pieces is not many of you want to write. There are some people in their private place, they are solving 400 questions every day. Money after night, 400 for the hits. So let's go. Is the Giga Muller counter. Niels Bohr. So when you look at it, Bohr in 19 good. It was the 1990s since model first. Good. According to Bohr, so according to Bohr's atomic model, he placed electrons in specific energy level. Those specific energy level is what he called orbitals. A region of space with higher probability to find an electron. And orbital is not where you find an electron. It's a place where there is high tendency of finding an electron. Now, according to Bohr atomic model, electrons move in definite orbitals around the nucleus, much like planets around the sun. These orbits or energy level are located at a certain distance from the nucleus. The farther you go from the nucleus, the higher energy you are occupying. So people heard this one now, started going away from their roots. Yes. Now, these are the Bohr's model of the hydrogen atom. Stationary states. Orbiting electron does not radiate energy. Now, listen. This thing is very simple. Just Jenny, then later when you look at it, you see now make plenty sense. Niels Bohr, his theory was to come into the field and show people the line of the orbital. That's that they always call it orbital. He tried to make them understand that what they think is orbital is not what orbital is. Oh, just a space People just think it's just a space, you just see electrons, just see this one. No, no. An orbital is a place, is a space of stochastic. Just that is a place controlled by high-level probability distribution functions, PDFs. So the thing there is this: if you believe that you can't find the electron anyhow, there are specific regions that you can see electrons. This is the nucleus. You see each of these lines? I see each of these lines. In real life, when you look at them, they are not lines, they are pieces. Now, what they are trying to tell you that you will never see it's impossible for you to see electron in between these two. If you must find an electron, there are specific regions within an electron cloud, which we will call the orbital. I know what I'm saying. Now, if you think that if an electron is here, and this electron is moving from here to this place, the electron moves from here to here, should be the electron is still in this orbital. He has not gained energy like that. He is still living within the same energy. He believes that your house defines you. Your location, that is the way atomic proportion looks like. That's what it looks like. See something. They believe that these orbitals contained specific amount of energy that they could contain. For example, I believe that the farther away the orbitals are away from the nucleus, the higher energy level they occupy. Now, let's manipulate the first energy level. Smallest, second, third, fourth. For example, it's possible that if you're on the first energy level, you must have 100 joules. You can't have more than 100 joules, can't have 100 joules. So any electron in that place has that amount of energy, 100. Then those in the second place can have energy of 200 joules. Those in the next can have energy of 400 joules. Those in the next can have energy of 800 joules. Follow me. If you stay within your own, you will have the amount of energy present in that one. So, what was he trying to say? He was trying to tell us and us that before an electron will gain more energy, what do you think he has to do? He has to jump from the present energy state he is and move to a new higher energy state. So, that thing is what they call transitioning. Transitioning. When electrons in one orbital jumps to another orbital, it's called transitioning. Now the question there is this: this electron, everybody, how many energy does it have presently? If you want to jump from here to here, how many does it need? Good. That if you successfully jump, you must have gained 400 made him jump to come and start staying here. Now, what about an electron that was here? How many does he have normally? If the electron want to jump and come here, what do you think you need to do? Does he need to gain energy or lose energy? How much energy does he need to lose? 400. You know what I mean? That energy that this guy has to lose when he's moving from higher energy level to lower energy level, they lose it in form of radiation. They lose it in form of what? That radiation, we call it photons. Photons. Photons means energized light. Photons means energized light. Now, see this formula here. This is the energy of transition. It's trying to tell you that when you jump from one energy level to another energy level, you can only do so making use of this quantization formula. A formula that helps you calculate and convert your energy value into something that's measurable. I guess what I'm saying now? Quantization into discrete values. Now watch. What's the formula for that quantization? Energy is equal to H. Very simple. Something you can do by yourself. Yes.
When it's attended this and you need to solve this, if you gave 50 joules, then like when you gave 50 joules of energy, you don't need to see the balls.
No. You see, no, you cannot give 50. Yes, that's how it behaves. You can, before you move, you have gained that number of energy you need before you can move to another one. Do you understand? And when see this thing explains darkness and light, I don't want to go there. I don't want to go to all those places. Because I want to say things and you will be thinking about things. Too young to be thinking. Say that again, please. You're too young to be thinking. So that's it. So there are two major spectrums that are formed from here. Watch. Two major spectrums that are formed from here. You have the what? Emission spectrum and absorption spectrum. What's the meaning of absorption? When you gain, so when electron is moving from higher energy level to lower energy level, is it going to be initiating an absorption spectrum or emission spectrum? You are going from higher to lower. What are you doing? Thank you. Emission spectrum, you are emitting energy. And that energy you are emitting, we will see it as light. We will see it as light. That tells you that when you suddenly, see, darkness can be defined as what? Absence of light. So sometimes we believe as scientists that if suddenly in a spectrum you just observe sudden darkness, it means electrons in some certain areas of that environment just did what? It just absorbed your light because they were going to jump from a lower energy level to higher energy level. So they stole the light energy and now you stay in darkness. Does it make sense? So you know what happened at the beginning of the world with flood and all. A lot of things. So everybody, it takes transition, jump, quantum leaps for you to gain energy. And classical physics cannot explain these quantum leaps or quantum jump. When I mean quantum leaps or quantum jump, I'm talking about transitioning. So this whole jumping from one energy level to another energy level forms what we call a spectrum. The form what we call it what? A spectrum. And we have, for your level, can learn like 5 spectral series. How to say learn 6? No. Use 5. You can use 5. What are the 5 spectral series? The Lyman series, the Bauman series, the Paschen series, the bracket series, and the P-Font series. If you want to go further, can learn the Humphrey series, the Satori series, down to where you get to the Fourier series. Most of those series are even mathematical functions. You will hear of the Taylor series and Maclaurin series. You will hear them. There are existing functions in maths. So let me write it down here. Now stop writing, just watch everybody. Why do we call this thing series? Because in each of those series, a series defines the level through which electrons in an orbital falls to. For example, if I'm talking about a series 1, it means electrons from orbital diagram 1 can fall there to 1. If I'm talking about series 2, only those above series 2 can fall to series 2. We're only dealing with the emission spectrum. You know, when you fall, you emit light. It's only the emission spectrum we're dealing with. So look at something. Let me imagine that this is 8, level 8. So I do like this. Level 8. Level 8. Level 7. Level 6. Level 5. Level 4. 3. 2. Everything like this, see. So when electrons are falling from higher orbitals to the orbital 1, the name of that kind of series is called Lyman series. So they can tell you an orbital fell from the first orbital into the Lyman series. What does it mean? It moved from 4 to 1. If they tell you, describe the first Lyman transitioning, it means from 2 to where? 1. Are you getting now? The series describes the final bus stop. So after the Lyman, we have the Balmer. So Balmer now, electron from the 8 will fall to the 2, electron from the 7 will fall to the 2, electron from the 6 will fall to the 2, electrons from the 5 will fall to the 2, from the 4 will fall to the 2, 3 will fall to the 2. We call this one Balmer series. We go to the third level. From the 8 to the 3 to the third. From the 8 to the third. From the 7 to the third. From the 6 to the third. 5 to the third. 4th to the third. We call it partial. Partial series. Bracket series. Somebody calling me. When you are moving from the 8th to the 6th, 7th, sorry, to the 5th. Let me go down more and let this simply. Those ones are going to the 5th. First, second, 4th. Third. So from the 8, so it's coming from the 8. So this one now from 8 to the 5, from the 7 to the 5, from the 6 to the 5. These are the P fund. This one is your bracket. This one is the P fund. As I said, you should stop for now. Okay. So, come on. Okay, you are done, Ali. Good. Good. So that's the date for Niels Bohr. So there are ways that they calculate all those radiations. There are ways that they can calculate the energy of the radiations that were transmitted. There's one particular one that they do. That one is the Rayleigh number. I said Rayleigh, sorry. Rayleigh's constant. They utilize the Rayleigh constant equation to determine the wavelength of a radiation released during transmission that will treat all these force. And what was that? The formula is 1 all over lambda is equal to RH, that's the Rayleigh constant, into bracket 1 over N1 squared and 1 over N2 squared. Where N1 square and N2 square are orbital levels. Okay, actually, after 10 minutes, I mean. So, okay. So, which one? This formula is for calculating the wavelength of radiation released during transition. Okay. Now, these things here form what we call a spectrum. The form what we call it what? A spectrum. A spectrum. Spectrum. What's the spectrum? See, you must have heard of continuous spectrum, discontinuous, all those things. Indeed, there exists. But there's some things in there that we'll talk about. Maybe when we come back from the break, I'll dive into it very well. The type of spectrum and all of those. But for now, we will be answering ourselves questions on the things we have done. Okay. God bless all of us who want energy. God. Today is Friday now.
Two hours to Friday.
3 hours to Friday. 2 hours to Friday. Yeah, don't tire. Huh? I confess. I'm not doing And I appreciate my organ. So those spectrums, when you hear what spectrum is an organized arrangement of frequencies. See, as a scientist, just the same way ladies see colors as numbers, we scientists see colors too as numbers. Go and buy here, they will tell you to buy color 32, color 21, color 15. We too, we see colors as numbers associated with a specific frequency. I'm being serious, no jokes. So, certain numbers are peculiar and programmed as the number for certain kind of colors in terms of their frequency. Yeah. So, a continuous spectrum is a spectrum that contains all. No, let me put it like this. Are you there? You know the meaning of spectrum, organized arrangement of frequencies, Abi. But when you now hear continuous spectrum, that one contains all frequencies of light. Contains all frequencies of light. So, the spectrums, we have the continuous spectrums, and we have the line spectrums. Some people call it discontinuous. All right. Well done. So, let me just do relay your mind, prepare your mind for this section. So when I come, you will receive it in the way it's meant to be received. So, the continuous spectrum, that one did, the same that one. The light spectrums, that's when we talk about those that are like dark lines on bright backgrounds, and we also have bright lines on dark background. That's right. Imagine you have a bright spectrum of light. When you are looking at it, you just have in between every color, you are seeing a dark line. I'll show you the picture. Let me do that here to make them bring out light spectrum. And the new get on. No. Look at the line spectrum. I think the design, how to design. Now image on a picture. Line spectrum. Or just tell her picture of a continuous spectrum and I want the boy to relate. Once he can relate to all those things, he don't have problem. No. No. Just type discontinuous spectrum or continuous spectrum. Continuous spectrum. See this one, bring it. Wait, see this one now, for instance. You see how all colors fade into the next. There is no demarcation. So it contains all color of light, but they are fading into the next. You see the other one now. Change. I see one now. See, yes. You see? Look at what do you notice about these two things? This one is colored line in dark backgrounds. The background is dark, but you are seeing bright lines. But this one is bright background, but you are seeing dark lines. So these two are line spectrums. This one is a continuous spectrum. Thank you. All right, thank you. Yeah? Yes, that's good. I'll use like Uh-huh. So this is where we stopped, the spectrum, the beauty of existence. Now, let me actually help you understand what's happening here with these two. Let me help you understand this now. Naturally, they were all meant to be like this. The continuous spectrum. That is how they're also meant to be. But you see all these ones that has line here. They call them absorption spectrum because once upon a time when they were like this, electrons along those lines jumped off. And they did not jump up to, they jumped off to attain higher energy levels. And by doing that, they needed to extract energy from places, Abi. So they abstracted those energy from certain regions in the line. And those, when anytime one electron do that, you will see it as these dark lines. You see that in dark lines. So that's what we call the absorption line spectrum. But this one, they were already dark. So what do you think electrons were doing in this place that were bringing those bright lines? The electrons were moving from high energy level to low. When you move from high to low, you are emitting, Abi. That's why they call it emission line spectrum. So when they emit, you see that a colored light. Do you understand? So that's how it is. So let's write. Have you written the meaning of continuous spectrum? But then, what about emissions and this? You've not written it, have you? So, right, line spectrum are of two types. Line spectrum are of two types. Number one, absorption line spectrum. Number two, emission line spectrum. Absorption line spectrum and emission light spectrum. So, right, an absorption light spectrum an absorption line spectrum is a spectrum formed such that it's absorption we're talking about, Abi, such that there are dark lines on bright background due to so that there are dark lines on bright background due to dark lines on bright background due to absorption of light. Absorption of light due to absorption of light from a line axis. Okay. From a line axis, that means from a specific line. Okay, the next one, emission line spectrum. Emission line spectrum. Emission line spectrum occurs when there are bright lines on dark backgrounds. And they are what? What I say there? Bright lines on dark backgrounds, are they? Good. Due to emission of light and due to emission of light. Stop. Okay. So, let me generate some questions that we're going to use under this topic to explain one or two things that I'm going to be doing the calculations. Because we said last series, those series we have to calculate the wavelength of the radiations emitted, the energy of the radiations. What is the formula I give you? E equals to HF. Then I also give you one that is what? 1 over lambda is equals to what? RH, which is the Rydberg constant to go back to 1 over n1 squared plus 1 over n squared. We'll be back to you on them. Let me generate these things. So then we're going to be solving those questions. Are you guys not writing? All this was your notes now, right? Okay? Mhm. So, that's what I'm still generating these questions. Is it on the load? Now, while it is loading, while they are loading, there's some things I need you to know. You can off this one because I will need the board. Need the board. Just off the projector too because that light will be born. So there's some things I want you to know. Uh, in this aspect, whenever we are calculating energy, sometimes they will give you energy in what we call electron volts. I said they'll give you energy sometimes in what they call electron volts. You can't solve in electron volts. You must convert to joules. You must do what? Convert to joules. Yes, so I want to teach you how to convert to joules. You understand? So basically, one electron volt is equal to 1.6 times 10 to the power minus 19 joules. That's all you need to know. You know what to do from there. They give you two, yes, they give you two electron volts. You know what to do to convert to joules. So you cannot work in electron volts. You can only work in what? Joules. And sometimes you can't leave your answers in joules. When you're just solving in joules, when you go to your answer, you have to report your answer in electron volts, the same conversion process. So you exhibits. So when I wrote this stuff of transition, you saw we wrote something A equals to H F. And let's take it. A equals to H F. I want to believe you know what H is. The Planck's constant, right? Very good. Let's just start with just 10 questions. I'll be solving this between myself. As time goes on, the brain will start turning to minutes. So, right, an electron falls from the third orbital to the second orbital. An electron falls from the n equals to 3. It falls from the n equals to 3 to the n equals to 2. So thus the n equals to 3. To the n equals to 2. Determine A, energy of each level. Energy of each level. Energy of each level. Then B, energy emitted. C, wavelength emitted. Three things that are applicable. Energy of each level. Energy emitted and wavelength emitted. So let's start. Firstly, I want to let you understand that we are calculating the energy of a particular level. There's a formula that you need to know. There's a formula that you need to know. The formula is this. Energy of any level is minus 13.6 divided by n squared. That is the energy of an n orbital. So if I draw one orbital for you, to calculate the energy, to calculate the energy of a particular orbital, you need to know the number of the orbital. That's what they will tell you. So once you know it, just put it inside here. But this one, you are reporting the answer. This one is EV. So it means when you are trying to solve this, you must change your answer to what? Joules. Do you understand? So the question says, we should calculate energy of each orbital. Which are the orbitals they are measuring here? 3 and 2. So we'll do it one by one. For n equals to 2 orbitals. For n equals to 2 orbital, A is equals to minus 13.6 divided by 2 is power 2 EV. I need to calculate minus 3.4 minus 3.4 EV. This is for E2. So what about for E3? Minus 13.6 divided by 3 is power 2. And as well as E3 equals to minus 13.6 divided by 9. E3 is equals to, yes, minus what? Minus 1.59 E 51 EV. Well, the formula is the same. And it's usually because we are following from coming from high orbitals to low orbitals. So you know that it's actually the loss of energy. So the negativity showing that energy is lost. So the next part says you should do what? It said energy emitted So obviously, listen, if you want to calculate, stop writing. If you want to calculate the energy emitted, you agree with that energy emitted should be equal to us based on moving from 3 to 2. Should be equal to energy at 3 minus the energy at 2. Right? So that gives us what? 1 EV minus what is 2. So the formula has minus and A2 has minus. So that's another minus again, right? 3.4 EV. So that gives us as 1.51 EV is 3.4 EV. So what's the value? 1.89 EV. And then you should be answer joules. So what will I do last? I'll do 1.89. This EV, 1 EV is what? So I'll just multiply this answer 1.6 times 10 to the power what? Times 19. Whatever I get is now joules. So that energy emitted is equal to what? Yes, 3.02 so times 10 to the power what? Minus 19. The last part of my question is usual for the what? Do we really tally? Good. How do we look the benefits? How do we look the benefits? Question number asks, most times, all those things you find them in between. Should be A is equal to HF. I mean, what is F? Frequency. F is frequency. And this F is still around. You know, so substitute still around to A now equals to us. HC over lambda. We want to look for lambda wavelength. So maybe we will subject for probably come. Wavelength now equal to what? Taking shadow. You see, imagine. You know that C is a constant. H is a constant. We've gotten our E already, have we? Very good. So, what are we writing? Let me teach you what I'm writing. I'm writing lambda is equals to H is what? 6.67 times 10 to the power what? And 64 good. Times what is the speed of light? Good. Divided by the energy of God, which is 3 times 10 to the power minus 19. So what's our answer, please? Six point 25 times 10 to the power what? Is a wavelength, so unit is what? Meters. G. So, electron falls from, this is another question. I'm going to open your spirit map today to things on things in things that can only be found inside physical things. But yeah, that's all. Electrons fall from where to where? Fifth orbitals to second orbital. Right now, it's a question. Question number 2. Electrons falls from 5 to 2. Determine energy release. Determine energy release. Determine energy release. B. Frequency. C. Wavelength. Very good. So let's go. What do you think we need to do? We need to know the energy of the fifth and the second. Then we subtract that will give us the energy released. So let's do this together. So we have N, which is equal to 5, to N equals to 2. So for the energy of the fifth, minus 13.6 divided by 5 squared, which gives me minus 13.6 divided by 25. So the E5 equal to direction minus 0.44 electron volts. E2 is equal to minus 13.6 divided by 2 to the power 2, which is minus 13.6 divided by 4. Let me get that. Minus 3.4 EV. What is next? E5 minus what? E2. That's what gives us the energy chain, right? That's what I'm saying. Minus 0.544 minus, that's minus resonance. Energy change is equal to E5 minus E2. What do you have on it? 0.544 EV minus 3.4 EV. That gives us what? 0.544 EV plus 3.4 EV. Then somebody 2.856 EV. Two point 856 times 1.6 and the standard power bands 19. Sorry, I'm going forward 1.57 times 10 raised power what? And 19 joules now. Another part of the question says you find the frequency. Find the frequency. Find the frequency. So, to find the frequency, I'm still utilizing words. We can just use E equals to HF. That will by H. That means F equals to D over H. Which equals to what's E? When you divide it, what does it equals? 4.57. 4.57 times what? Eh? No.
So it's 8.1.
6 times what? 10 what? 13. 14 hands. What do we have? Wavelengths. What's the wavelength? Can you get the wavelength yourself? I do the wavelength. What does it do? How many each? And we have wavelength equals to VC over E, which we utilized before. And then this was 6 times 10, it's 4, 3 times 10, whatever. What's that?
Okay.
What? Electron moves from first to fourth orbital. First to fourth orbital. Determine A. Initial energy.
Hey, what?
A. Initial energy. B. Final energy. C. Energy absorbed. D. Frequency. F. C. Energy absorbed. And D. Frequency. So we are looking from where to where? We move from ground state, that's 1 to 4. From n equals to 1 to n equals to 4. So the energy of the first one is 3.6 in the ground state. And the fourth one is 3.6 over 16 kJ. When you divide it by half, yes, it's 5 divided. Okay, so what the next thing to do? So the change in energy was from E4 to E1. So that yes, what is plus, yeah. Uh, Yeah. What's the value? What is it? Looking for the frequency, right? Frequency. Frequency is equals to mu over h. Okay. 3 points. Next. Determine the wavelength for, we look at now, right now to dictate. We are not interested. I'm not interested yet. Right one. Você studiare ragazzi. You can go outside. Okay. Are you ready now? Anyone? Determine the wavelength for. Determine the wavelength for. for transition from n equals to 6 orbital, transition from n equals to 6 orbital to n equals to 2 orbital. Yes. And I know the wavelength from 6 to 2 using Rydberg equation. Using Rydberg equation. Now, Rydberg constant is 1097 times 10 to the power 7. Rydberg. When I give you the equation, I wrote it. So, what's the Rydberg equation again? 1 over wavelength equals to Rydberg's constant put at 1. Right? Okay. So, what are we doing? We're having, follow me. 1 over right, this equals to, what's the Rydberg constant? One over. What's it going to be? No, that represents where you are coming from. No, you are coming from. Sorry, where you are going to. He says move from the 6 orbital 2 to 2. So he ended at 2 away. That's it. But let me even, please, you can write it in the formula as final so that you don't be confused. Final, initial. Do you understand? Use the word final and initial instead of numbers. Do you get it? Good. So what's the final line point of this one? 2 raised power 2. And this one is what? 6 raised power 2. Yes. So 1 over lambda is equals to. Do the bracket only. The bracket. 0 point. For inside the bracket only. 0.22. And then multiply this one. Multiply. Multiply. So 1, I think 2, 4, 3, 7, yeah? 0.778, right? Is that that's not the final answer because this is 1 over lambda. So do 1 over answer, just press 1 divided by answer. That will give us lambda, the inverse. So what does that give you now? Correct. Yeah. 4.10 2 times 10. Yes. Let's go. Number 5. Let's go. Electron flows. Let's go. Electron flows from the fourth orbital to the first orbital. Electron flows from the first fourth orbital to the first orbital. Determine electron flows to the first orbital. Yes. Determine energy released. Determine the energy released, the frequency, and the wavelength. So we're looking at the electron falling from here to here. So what we're going to do is falling from n equals to 4 to where n is equals to 1. That's the ground state. So the energy at when it is 1 is minus 13.6 divided by 1 squared. Then we run on this formula to obtain energy of a particular shell. So this is in EV, and we don't solve in EV, we solve in joules. To convert EV to joules, we multiply it by 6 times 10 to the power minus 19. That's what I can say. So from there, I can say E1 equals to minus 13.6 EV. When you convert it, what does it give us? Okay, don't worry, just do that like that. E4 becomes minus 13.6 divided by 4 squared. Minus 13.6 divided by 16. Will you ask me how? The formula has squared, that's way. Alright, so E4 is now equal to EV. Then I go see. Yes. Minus 0.8 EV. So that is the change in energy or the energy liberated is equals to the E4 energy minus the E1 energy. So the change in energy that is equals to minus 0.85 minus 6 EV. What is it? I can't hear you. So what's the next? And what? We have to get the jokes.
That's 2.04 times 1 minus
2.04. So the set shows what happening frequency. How do you get that?
minus 3.05 is minus
Can't be 3. Wavelengths. Wavelengths.
equals to HC over lambda.
That's too far.
Equals to 3 times 10 raised to 8 over 3.05 times 10 raised to 15.
What does it give us? 9 points. 9 times 10.
That's all. Next question.
Right. Photon. The photon wavelength of. Sorry, the photon has the wavelength of. The photon has the wavelength of.
Wavelength of
No. The photon has the wavelength of 6 points. Sorry, 656.3. 656.3 nanometer.
okay.
Find energy.
We are using E equals H2 or lambda. Ten raised to power minus 24 times 3 times 10 raised to power 8 divided by 656.3 times 10 raised to power minus 9.
The answer to 100. 3.03 and still divided by 30.
3.04 times 10 raised to power minus 19 joules.
Combine the numbers together, the total derivative. What's the joules?
Times 1.9 times 10 raised to power minus 38. Okay, next question. Next question.
Okay. Can a photon of wavelength
Sir?
of wavelength 97.3 nanometer excite hydrogen?
Sir? Can a photon of
Can a photon of wavelength 97.3 nanometer excite hydrogen?
7.3 nanometers?
97.
Okay, 97.3 nanometers.
Excite hydrogen from excite hydrogen from 1 to 4. Come. Minutes. Minutes. Hope please. The camera is on. Hope is visible to on the timer. I don't get the timer off. Because now, yes, the camera is on. Photon of the exact hydrogen from one to four.
But
Yeah.
it's 4.
Okay, so dividing this is what?
You get minus 0.85. E. But change E equals E4 minus E1. When we convert to joules, change E equals to 4.756, 1.3 carries for minus 9. And we get 2.04 series for minus 8 joules.
Rho is the required energy. And the energy available from the photon is 9 what again? Sure. 97.3 nanometers.
Yes.
97.
0.3 nanometers.
Let's check out if that's sufficient. That's the frequency. So I just have to say is equals to HF. So 6.6 times 10⁻⁴ times 7.3 10⁻⁹. So E is equals to what?
So it's like because that's or with
Almost. And F is equal to this. H is this. Okay, it's wavelength. So is equals to C lambda.
and 7.3 times 10 for minus 9.
Thank you. So we have. I think we're going to do the exam.
2.034. 34 joules. Oh.
So it's exactly sufficient to cause an excitation. So it's exactly sufficient to cause an excitation.
So from that other, from what we got before, we got 2.04 times 10 to the power minus 18. But 2.04 times 10 to the power minus 18 is not equal to 2.034.
Yeah. It's what people call I was writing. It's what you call I wrote. It's what you called for me I was writing now. Which place exactly where? You people are calling answers I'm writing now.
Okay, next question. Next question.
I don't know. Yeah. Yeah. All right. So there's a question. There's this question I'll give you. We're going to be applying cascade transition to see what we can do enough of the beans. The hydrogen atom. The hydrogen atom is excited. Is excited to the n equals to 8 level. Is excited to the n equals to 8 level.
Okay.
and eventually returns to the ground state.
Okay.
Determine 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 the total number of different spectral lines that can be emitted. The total number of different spectral lines that can be emitted. The number of Asian series lines Asian series line. C. The shortest and longest wavelength emitted. Yeah, that's it.
Okay, so how are we going to go about total number of different spectral lines that can be emitted?
You started solving it. What are they? What are you reading now? That's what you are reading. Attempt it first. For your ask me. And it's very simple. You just English. Total number of different special lines that you can see there.
97.
What did you use that? You know how to calculate number of spectral lines. You don't know how to calculate number of spectral lines.
No, sir.
You use capital letter N equals to small letter n, open bracket, n minus 1, close bracket, divided by 2. The number of spectral lines equals to n, small letter n, open bracket, n minus 1, close bracket, divided by 2.
Why is it 21?
How do you get 21?
Then she use capital letter N equals to N into brackets N minus 1 divided by 2.
You get it 21. How do you get it 21?
My N is 7.
Read your question.
A hydrogen atom is excited to N equals to 8 level.
So
And
N
eventually
equals to what?
8 level.
So your N is how many?
So I should use it.
Yes.
$28. The number of partial series line.
So what's the answer to that one? Right?
You don't have to go about it.
Did you think about anything? As I've been in one, you don't have to think again. The brain is for thinking idea. Think. What did the question answer? The number of what? I can have from there. The orbital, the maximum of the orbital number is what? The maximum orbital number in the question is what?
It's
So that means electrons can fall from any place except from anything that above it to action. That's the meaning. So many spectral lines are going to be in that. The maximum orbital they are falling to business falling from this question is what? 8. Passion is already in over orbital what? Passion is orbital 1. What are your spectral series? I'm reading them from the first one. The first one is what? Like 4 to 3, 5 to 3, 6 to 3, 7 to 3, 8 to 3 is where you stop because the question is from 8.
25.
Yes.
Okay, so we're solving the next one, the shortest and longest wavelength everything.
The longest will be which one? The longest will be which one? The longest wavelength everything will be what? From what of that rocket?
7 a.m.
Any plan?
Yes.
Your longest wavelength expected should be from what orbital to what orbital?
From 3 to 8. So 1 to 8.
1 to 8. 1 as plan.
Said eventually return to the ground.
You know the other thing.
Yes. No states.
Then that is shortest. You know, energy as you move higher in these orbitals, their energy is increasing. Energy is inversely related to wavelength. So don't let the increase in the number deceive you and think that that's the number one. The shortest. The longest and those ones that will be closer. Okay, my next.
So, can you say about this? Is it shortest and longest wavelengths emitted? I'm looking for values.
Every moment.
Are we looking for values?
What did you do for my idea or what? Well, everywhere. The values justify your choice. You want to just tell them this and this. Nice one.
Okay, so next question.
Okay. Okay. All right. All right. All right. So let's get them into it.
Okay, so for the shortest wavelength, for the shortest wavelength, I got 9.34 times 10 raised to the power minus.
Okay.
Can I tell the answer?
I just said, okay, so like I'm checking that kind of okay.
Uh,
So what's the value?
I got 9.34 times 10 raised to the power minus 40.
That was for your shortest wavelength, Abby.
Yes.
How did you do it? Speak boldly, please.
Okay, so what I did is that say the shortest wavelength is from N1 to
I'm talking too much. What you did now then? It's not the method. Change the method. What's the name of the method? And the thing is really, the usual is write the equation. Do you know?
duration.
Right there. You know what I'm saying? I want to be sure you're not using something stressing you. So that when the exam comes, you don't go and start stressing yourself. Right there gives you that numerical proof immediately. So
So the right way is constant 1.097.
that's times power. So
Punching our calculator. So this for finding the shortest, right? How do you find the longest?
the longest is the one that is farthest away.
That's
The longest wavelength was closest to 8 to 7.
it. So I got I got minus 9.29 times 10 raised to the power 8. 8.
You did rubbish. You know you did rubbish.
And my N2 is 8. And my N1 is 1.
Your N1 didn't.
My N1 is 1 and my N2 is 8.
I thought I said 8 to 7.
That is for the shortest.
8 to 7 is the longest. 8 to 1 is the shortest. As the longest. As the what? You and I are not speaking the same English. Oh, yeah. I just finished drinking.
I'm coming.
Hmm? Are you guys ready? Why are you beating? Is that the answer? Are you guys ready? Ready now? Can you give my next question? What are you waiting for? Eh? Okay. No, okay, go. Jesus. What did you say? For the short, you go. That's the shortest wavelength. I think I put it for the long. You are doubting when I told you that that would be longer. When I solve it, I see it's going to be longer or shorter than what it was. Because if we are looking at it 8 to 7, 8 to 7 is not shorter. And 8 to 1, the distance is long. We are solving, it's not making mix.
The next question.
Have you gotten it? Solve it and see the numeric value. So, can we move now?
For the other, I got 1.905 times 7 to the power minus.
So which wavelength is longer?
So this is longer one.
Which wavelength is longer? It's the longer one.
1.905 times 7 to the power minus 5.
So I was saying rubbish. Now I'm writing. The hydrogen atom is the second energy level absorbs
The hydrogen atom
in the second energy level. Absorbs a photon of wavelength. It's 5.0. 85.0. 85.0. Mm. Determine the photon energy and the ionization energy from n equals to 2. From n equals to 2.
from n equals to
If analyzed, the maximum kinetic energy of the emitted electron. That is another line. Yes, maximum kinetic energy of the emitted electron. Shit. If analyzed, the maximum kinetic energy of the emitted electrons. It's more. Of the emitted electrons. A speed of the emitted electron. When I done with this question, there's something very important and deep I would want to get you guys involved with.
electron.
That's all.
That's all. Okay, so we got to find the photon energy and the ionization energy from n equals to if ionized the maximum energy of the emitted electron.
The depth of who we are and find peace with what we become. Now, what is in my head? Oh, yeah. Oh, finish first. Fast.
6 hours.
Start for you. Start. What does this do? Goodness. This is in the club. My eye just do open. I don't off. Oh, Jesus. How you doing?
For my photon energy, I got 0.235 times series for minus 6 joules.
I'm sharp. Are you guys done? Are you guys done? Are you guys done?
So for my photon energy, I got 2.35 times 10 raised power minus 7.
What?
Photon energy.
What question did I give you?
You asked a hydrogen atom, the energy level absorbs a photon of wavelength 85 meters, 85.0 meters. Determine the photon energy, ionization energy from N equals 2. If ionized, the maximum energy of the emitted emission.
Sir. My answer was what?
For photon energy, I got 2.35 times 10 raised to power minus 27. For ionization energy, I got 1.632 times 10 raised to power minus 18 joules.
I like your confidence. So what's the photon energy level? Your A, the answer for A.
2.35 times 10 raised to power minus
Minus 16.
Minus 16. I said 27.
What did you divide last?
Over 85.
Just what was your previous division before that time? You know, you didn't document your solutions, right? Is that not a bad thing to do? Yes, seriously, you're not documenting your solution. For a step you don't know, if you know it yet. If it's that you use this step you're confident about, you can skip it. But you're not confident about it yet. You don't know if you are correct. Okay, how do you want me to correct you? To stand and walk and come and show you. I don't know, you made errors to your exponent obviously because it's times 10 to the power minus 8 times here. Children. Yeah. Yeah. Yes, what's the answer? You guys have 2 minutes to put already. I'll shift you guys now. If you guys are not responding in 2 minutes, I'm going to shift you people. I'm not joking.
So we use E equals to H
I want to see the
over lambda.
solution.
We use E equals to H over lambda. Now H is
When
6.67.
you say the solution, you are trying to sensitize my auditory nerve. I want to see the solution. Yes. Yes. Just pass it. Did you figure out your error? I think there's a water in this. They just this is you have 1 minute to redo it. 60 seconds to redo it. I'm coming. The 60 seconds if not done. You can go and sleep for the night. Just go and sleep. You are observing cameraman. You're not doing anything. Where are your rough works? Where are your rough work? Your rough work, your rough work. Because this cannot be everything I've been doing since. Where is your rough work? This is something I'm doing. Just this one. What? So, okay, I'm not gonna simple. After telling me that this is what you did, you have come on now and sharp. I told you I should be here in better minutes. Yes, still atomic structure. You suppose don't take electromagnetic induction. You suppose don't take analysis circuit. You did 29. You did 29. My, my like 10 years now. That day I saw it. I should check the answer page. It was supposed to be base power minus 18. Let me check. What is it? You got 2.3 something that times power minus 16. You were supposed to be minus 18. Talk now. I mean, I know you're hearing me. What was what? Do you feel they made an error? So HT over lambda. Minus what? Eh? Mm-hmm. Eh? It's 5 nanometer. Use your common sense. Can the wavelength be 85 meters? Do you know the meaning? Just one cycle should be 85 meters. Won't you be seeing it? Without it to be. But you know, in the front of that book. That book might be. You have to collect all of his certificates. $10.2 EV. I'm wrong.
So is it minus 3.4?
Minus one.
Minus 3.4.
It's not minus 3.4, it's plus 3.4.
It's plus 3.4. You actually go minus 3.4.
I'm with you.
We use the formula minus 13.6 over n squared. Our n is.
Do you realize it's only one question per done?
Yeah?
It's only one question per done since. It's one, it's the babies that you have been dealing with. When do you think you do like playing? I'll be like, go get out of this place. What? Finish this thing fast.
So how do you get 3.4?
I did I get what? You just told me you got 3.4. You got 3.4, you asked me I got 3.4.
This is way sure.
Audience, boss, there's no audience management around. All these ones, they're no audience. All these ones are no audience.
Hi guys. Energy of what? Oh, you have already done all the other ones. Please, carry me along with this village. Your answers. Yes, carry me along with your answers. Yes.
0.2775.
That phone number, what? What are you calling? Is it number what?
K, that is the energy of each emitted photon.
Uh-huh.
That is 0.77 eV. 270.
What you're calling from, is it is it transition from 7 to 5? Which one is that number? Wait.
That is 7 to 5. I got 0.3319.
You're wrong. You're wrong.
That is transition from 7 to 5.
Okay, that's the transition. You're wrong. That's what I said. How did you do it?
Transition from 7 to 5. I use minus 30.6 over n squared.
Your N was what?
My n was 7, the other was 5.
And you now got what?
I got 0.331.
Now carry the calculator again. Yes, yes. Oh. Hello. No. Chief, I can always myself. It's too far. It's too far, 18 minutes.
Okay, so we got 0.697
For which one? Okay.
So I'll give you a question about it. I got 4.65 times 10 raised to power minus. So I got 4.65. So I got 4.65 times 10 raised to power minus 6.
Okay, but what is doing this? What's the
For the other one, I got 1.281 times 10 raised to power.
I still found the kind. Is that enough hands?
So,
Yeah.
for the first wavelength,
I'm looking for it. I'm looking for it. Okay. So which one are you calling answer for me? The one that was what? The thing is to calculate ionization energy from it. Does ionization go? Maximum kinetic energy.
you should just calculate the energy of each emitted photon, the wavelength of each, and the total energy emitted. Yes. That's the last question.
Yeah. Translational one. Yeah.
Yes, that's the last one. In the present.
So that is
Energy of each emitted photon. We have 0.267 eV and 0.96 eV. Then for the wavelength of each proton, we have 4.65 times 10 to the power minus 6 and 1.281 times 10 to the power minus 6. Is it correct?
they're just calling numbers. This the N5 is what? N5 for the energy. No. Uh-huh. You don't even 0.0544. 2.544.
Okay, so for the N7, I got 0.277. For N5, I got 0.544. And for my N3, I got 1.51.
It's correct.
So for my wavelength of each photon, I got 4.65 times for minus and 1.281 times 10 raised to power minus 6. And
Okay. That's correct.
for the last one, the total energy embed, I got 1.233.
1 point. No. No, that one is wrong. Total energy. No.
Two point three three one.
Yes. 2 points.
331 EV.
No, no, no.
Should I convert it to joules?
I know how to convert it. No. The answer you called in. The correct answer in joules is 13.322. Why are you missing it? Because add all the energies. Is it not for you to add all your four energies? Anyone.
That's 2.331 EV.
2 points. Huh? I'm going. Okay. What are you guys doing? What?
So what did you say you got for your total energy?
13.322. You guys are stressing me out. What is this? How can you get all those other values and you are not getting just to add all those things you mentioned? So why not getting the correct answer now? Where are those values you could? I mean, what's the thing you're supposed to use and then add? And the total energy. The total energy is 13 points. Hold on. Hold on. 13.2. It's 13.2. It's 13.2 as well as we get it.
Summation of 0.277, 0.54, and 1.5.
Is it the three energies that you have? How? The transitions, how many did you mention?
7 to 5, 5 to 3.
That's all. That's all you heard. But that's not what I said. And one of the values here is not even correct. 0.266.
0.277, 0.544, 1.51.
I don't know. Is
So what are the values?
0.266, 0.967, 1.889, 10.20. Did you do what? What do you calculate? What do you calculate? The values you called that time not correct too. I did the same what I just called.
0.67, 0.267.
Did you mention anything 0.67? 67. What is it? Your second value is what?
0.967.
Your third value.
So when you say the size should be, is it 7 to 5, 5 to 3?
What was the next value after that 0.967?
Living.
Just now call it.
0.697. 0.267.
That 0.697 is not correct.
0.967.
That one is correct.
0.267.
Still correct, approximately.
Approximately.
It's correct. That one is 0.266. Continue now, make I know your error the power. It's 4 energies.
7 to 5 to 5.
What is just the word? I don't like when people just the word. Ask you. I know how many times I repeated this thing. The extra. 7 to 5, 5 to 3, 3 to 2, 2 to 1. There's only 4 that was absent. Come on. Use how many hours to answer one question.
I got 1.88.
1.88. You know the thing that's bad for me? You think I'm just listening, I will get angry with you soon. You're 1.88. To which number? You know how many things what number are we talking about? Yes, 1.88. Which is even actually 1 point. Your calculator gave you 1 point what? So when you now pick the value, you now pick 1.88. When you get 88. When you want to pick that, it's not 1.889. So why do you pick 1.88? Even if it's only 1.88, you would have mentioned 1.89. But in our mistakes, they pain my brain. Yeah. Yeah. And why the thousand people know the audience? I don't know what's doing them today. Since we have been doing one question. Doesn't point what? Everything all together, Abi. Good. So we can go to another question now. Should I go to? Because I'm scared of going to another question. No? I'm standing here, people are laughing my front. I ask you a question, if people are laughing my front. I'm not saying it again. It's not my time. The spirit, I'm gone. Somebody is playing me. A question. I'm not serious. Right. Hydrogen atom. A. Now you are seeing you. Later you tell me there is something you know here. Be creating personal interference. Say, Bob, you have problems. Right or you, right or hydrogen atom. A is in the N equals to 5 states. Hydrogen atom B is in the N equals to 3 states. I did not mention 4. I did not mention 2. 3 states. Both returned directly to the ground state. Not both returned. Both returned directly to the ground state. Determine the energy released by each atom. Determine the energy released by each atom. That's not all. B. Which emits the higher frequency? Which emits the higher frequency? C. The ratio of their wavelengths. The ratio of their wavelengths.
For the energy of the adult 13.05.
Hydrogen for
For the energy of the adult 13.05. For me, I got 12.087.
hold on. For A. What did you say you got again, please?
I got 13.056.
Okay. Step. I've been replying since. It's minus 13. Minus. See what you just did. You just put minus straight. Why do you put? Oh, yeah, what's the reason for the minus? Just wait. As you just put minus at the end, does it your previous workings does it go in line with that final answer with minus? So you just carry minus and add put. Boss, I want to take my break. The headache.
0.925.
Yes.
Next question.
Okay. All right. I'm here.
Next question.
Are you there?
Yes, sir.
A resistor of 4T. No, sorry. Yes. A resistor of 40 ohms. 40 ohms. Comma. An inductor of 0.20 Henry. An inductor of 0.20 Henry. And a capacitor of 100 microfarad.
Capacitor of
Capacitor of 100 microfarad
yes.
are connected in series.
Are connected in series.
Yes. To a 50 hertz, 240 volt supply.
To a 50 hertz,
240 volt supply.
240 volt supply.
Yes.
Okay.
Find
Find
A. Inductive reactance. B.
B.
Capacitive reactance.
C. Or is it any C?
Yes.
A C.
Resonance frequency.
Resonance
Frequency.
So is that all?
No.
Okay, G.
Admittance.
Start come again.
Admittance. Lastly, find all susceptance. Find all susceptance.
So is that all?
Yes. Alright. Alright. Yeah. What's it? What's it for which one? Yeah. Hello. Huh? I'm going to Zoom to you. Eh? What? Listen. Don't worry. Stop. I mean, I've not done this all. No. Okay. So which number are you guys doing now?
Because
Have you guys done the independence? Have you done the independence?
No,
What number you need?
resonance frequency.
Okay.
$11.2.
They're just calling the value. They don't like inside their listing. They're about. You know, so I'll check it later. I'll check it on later. Jansen and all right. So yeah, I don't know those ones. I mean.
Have you seen the answer for resonance frequency?
Yeah. Once you use the appropriate approach, you'll have a problem.
Use Excel. And then frequency might be.
Mhm. All right. So we're going into the next thing. Now we're going into elements of modern physics. All right.
Elements of modern physics.
So yeah. So along the lectures, we're going to be covering the following.
Sir?
Along the lectures, this lecture, we're going to be covering the following objective. Quantum theory. I think that's where we're going to be starting from. That's like our starting point. We'll be running through the quantum theory, explain wave particle duality. We'll talk about black body radiations.
Talk about
Black body radiations. Then we'll explain photoelectric effects.
photoelectric effect.
Describe Compton scattering. Explain Bohr's atomic model. We'll be talking about matter waves, uncertainty principle. Then the Schrodinger equation for wave mechanics. Atomic spectra. Those are the things we'll be touching. Yeah. So when you hear the word modern physics, what comes to your mind? Modern physics. Okay. So basically, physics has been classified into two generally. We have classical physics, and anything classical physics does not explain. Modern physics has been able to explain it, making use of a different approach to solving physics problem. So the whole of modern physics comprised of the following branches. Number one, so you're writing branches of modern physics. We'll be looking. So the branches of modern physics, we have quantum mechanics, relativity, atomic physics, which has been done,
And
nuclear physics, particle physics. Then solid state physics.
branches of modern physics, quantum mechanics, relativity, atomic physics, nuclear physics, particle physics, and solid state physics. Is that all?
Yes. So eventually, after the discovery of modern physics, that's just scientists got to understand that Pascal physics was a failure. Especially when it came to aspects that has to do with atomic stability, atomic spectral Compton scattering. It didn't share any light. So till today, there are so many explanations in modern physics that disagrees with classical physics. But we're not going to be shining this agreement into the light.
So when we hear the word classical physics, let's just first of all differentiate between both. Classical versus that's different between classical and modern physics in the table. What's it? Number one. Number one. Classical physics was always emphasizing on continuous energy. It emphasizes on continuous energy. It emphasizes on continuous energy. But modern physics emphasizes on quantized energy. Do you know the meaning? What it means is that classical physics has made us understand, or should I use the word, has given us the perception that energy is everywhere, that we are constantly transacting with energy and stuff like that. Why quantum memory physics is making us understand that energy is quantized. Like, you actually don't have to be just finding everywhere. They are in packs, the discrete measured values. You understand? So another difference is
Another difference is
classical physics is deterministic. Classical physics is deterministic.
is
It's deterministic.
what about modern physics?
Probabilistic.
It is
Probabilistic. It works on probability. Nothing is 100% certain. And again, another one. Classical physics emphasized on particles only. Everything you did there was particles, particles, nothing, no waves. Except for wave as the topic, no wave.
okay. So classical physics emphasizes on particles only. About modern physics.
Modern physics emphasizes on wave particle duality. And lastly, particle physics were working with absolute time. When modern physics, we work with relative timing. What's it? So, have you written it? Okay. So, the first thing we want to talk about is the quantum theory. And that was proposed by Max Planck. Max Planck. He proposed the quantum theory. He proposed and when we say he, I mean Max Planck himself. But he is the, let me first write it there, introduced by Max Planck, where he proposed that energy are released in discrete parts called quantum. So yes, to the point knowledge that he was able to put forward an equation that works to calculate the amount of energy available or that can be released, I get me now, per any energy kind of dependent process. So it was not just that energy is a continuous thing. There is an amount of engagement that will require a certain discrete amount of energy to be accessible. And it was all confined under the equation E equals to HF. This equation shows us that what? A frequency is a major determinant as to what the energy can be. So these quanta were usually seen as photons. We see photons energize light. Seen as photons, they are called energized light. Photons. Yes. Where are you? Usually seen as photons, which are referred to as energized light. They are referred to as particles of electromagnetic radiations. So don't get it twisted. Photons are not radiations. Nominally, this is what they are known as radiations. Photons are not considered to be waves. Are you there? Said that photons are the what? Particles of what?
electromagnetic waves. So it means that photons are the forms in which energy are absorbed or emitted. Stop. They are the particles of electromagnetic radiations. So let's discuss some of the properties of these photons. Because in your exam, they can just ask you to state some of it. Properties of photons. A photon bears zero mass. They are massless. Yes. Precisely like what we refer to as rest mass. You know how rest mass. Are we there? Another thing is that, I call them arcs of light that are energized. So that is they move with the speed of light. Zero rest mass, right? They carry energy. They carry energy. They are energy carriers. Carriers of energy. What other thing do they carry? They are also carriers of momentum. So, in what form do they carry energy like this? In what form do they carry momentum? They carry momentum how? Think wavelength equals to h over mv. That is over this. They carry like this. So, we go into wave particle duality. Wave particle duality. Wave particle duality. Wave particle duality. So the wave particle duality describes that light can behave as both a wave and a particle good. So the wave particle duality, it describes light as behaving as a wave and particle. Which other thing do you know that behaves as a wave and particle? Which other thing aside from light do you know behaves as a wave and particle? Just right. This also stands true For who? For electrons. Because electrons in themselves are beginning to be considered as what? As waves. They've also been able to be considered as waves, you get, and also particles. Black body radiation. Black body radiation. Black body radiation. So, what's a black body? Okay, very good. Let's write it. That's it. So, right, a black body is one that absorbs all radiation. Here's the way I'm going to put it. It absorbs all radiation and emits all wavelengths depending on temperature. All wavelengths. I'm coming. Black body. So yes, I said that this black body is one that absorbs black body is one that absorbs all radiation and emits all wavelengths. At what? At specific temperatures. So the temperature is actually a major part as to that happening. You get? So that process depends on temperature. Yep. Yeah. Because sometimes, wavelength are actually relatable with frequency, yes, but when they use frequency, it means that they can give it off as energy. They can give it those, like when we said they absorb all radiations. That radiation there is keeping note of the fact that these things are energetic. But emitting does not mean that we emit them or release them in energy form. You get? And just be released in particulate form and stuff like that. So there are some predictions in classical physics. In fact, a major one is the Rayleigh's prediction of energy being present at all wavelengths or being able to keep impacts infinite amounts of energies, and found that eventually when he tried to experiment, it would not work. You get? So stuff like that is one of the major classical failure that has ever occurred. So those were classical predictions. Classical predictions. Let's recover on this thing. Fast calculations. Right. Rayleigh-Jean's law predicted Rayleigh-Jean's law predicted infinite. It predicted infinite what? Infinite ultraviolet energy. Believe that you can have a broad spectrum of energy and will be visible within the frequency of normal visible light. But upon experimentation, it was the other way around. Before even getting to ultraviolet, the peak of the measurement, the peak of the whole experimentation had disappeared. They only saw the returns. You know that initially you will get at very low wavelengths high peaks, and the peaks will return now. So they didn't see the peak of the ultraviolet light. You know, it's Roy beef. The final one is the violet light. So they didn't see the peak. So obviously, I don't know, they must have repeated it many times and found out that, okay, it's like this is normal. So Rayleigh-Jean's law predicted infinite energy for ultraviolet light. But upon experimentation, they obtained, no, they obtained, it failed. It failed. They were not even obtaining anything. It failed. So it was the failure that is now tagged as ultraviolet catastrophe. So I'll just put it there. This became the ultraviolet catastrophe. Are we there now? Are we there? Okay. So, Planck's solution. Planck's solution to this catastrophe. So it was after this event occurred that Max Planck had to put out a prediction there, as stated that energy is stored in discrete packets. Yes, that was when he came up with that statement. You get it now? So he put forward equations, one of which was the E equals to HF. In fact, normally, that equation was written like this. E equals to NHF. That was how it was. Where N was an integer that controlled the number of packets of. You understand? So it's just we that eventually found our way to using this way. Do you get it? So that was that for that. Then I want to go into Rayleigh's displacement law. I want to go to Rayleigh's displacement law.
Now, what this guy's postulate states? He stated that I just listen so I can understand. So that as maximum wavelength, maximum displacement. Because you know that the issue with the catastrophe something was that at short wavelengths, waves or radiations were reaching peak intensities. I think I showed you that the other time when we were having the private sessions. That show you a graph like that. Eh? So, you know, the one that happens for different equations that will mitigate it. Or that could, that is what cushion for that lapses of getting to peak intensity at short wavelength. Because whenever they get to that peak intensity at short wavelength, it reduces the quality of the radiation, energy that have been transformed into different forms. So what usually used to be available for the remaining part of the reaction is usually something very, very small. That's right. Then the displacement law shows that at maximum wavelengths, at max wavelengths, which we do like this, the product of the maximum wavelength and C is directly proportional to B. In fact, the constant is usually 1, so just write equals to B. Time, yes, equals to B. So time, temperature, I mean. Wavelength, temperature, you know, is the intensity we're working with. Right? B. Where B is the Rhien's constant. Some people call it the Rhien's factor. 2.898 times 10 raised to the power minus 3. 2.898 times 10 raised to the power minus 3 meters of K. So what was the resolute? That started making hotter, because the issue was hotter object at high intensity. It gave other objects much shorter wavelengths. Are you there? Which give them a characteristic blue color. Stefan Boltzmann's law. So Stefan Boltzmann's law Stefan Boltzmann's law described relationships affecting how what? How is Stefan Boltzmann's law? It was just Stefan Boltzmann's law. Eh? Hmm. Is this your first time hearing Stefan Boltzmann's law? I mean, I just finished one side. Yep. Eh? I still don't have to sleep. I still don't have to sleep. Right.
Stefan Boltzmann's law.
In terms of amount of power dissipated from a radiation, in terms of amount of power dissipated from a radiation, the total amount of power, the total amount of power emitted is equal to
Power emitted.
P as equal total amount of power dissipated P is equal to the right hand expression like this, T raised power 4. So in our practical model physics, what we are concerned with is this P that varies with 4 like this. That's what I'm more concerned with because the issue there was once you raise the temperature of certain materials to high temperature, subject them to high intensity, they tend to fade out or use what phase out completely. You don't even see them. This is not about a change of state. It will look like they were never there. So that was the reason why scientists started moving into the field that studies heat, temperature, intensity, not as classical physics, modern physics. So after that guy worked, the next person who brought success into that field was Albert Einstein in his photoelectric effect experimentation. So yeah, what happened in photoelectric effect? The idea of photoelectric effect was about what does it surround? So the concept of photoelectric effect, that what? Hello? Okay. So the idea of photoelectric effects is that when incident ray possess energy strikes a smooth metal, they do something to the metal. They energize the electrons in the metal, cause them to excite. When energy or should I say conditions are in place, it will also further knock them off. Knocking them off means that what the electrons get liberated from the surface, right? So we now want to look at what are the properties of the radiations that are responsible for giving us high amount of energy on the surface, or more or less increasing the number of ejected electrons. That's what we're looking at. So let's go there. Right, photoelectric effect. And this describes how light incident on a smooth metal surface. This describes how light incident on a smooth metal surface causes ejection of electron. Cause ejection of electron. Okay. So we are looking at it this way. So what I'm saying there is that electrons are naturally interlocked. They are naturally interlocked within surfaces. And the truth is that it will only take heat energy to loosen up some interlocks. It will only take heat energy to loosen up some types of interlock. Yeah? I said it only takes some kind of energy to loosen on some types of interlock. So I'm saying that when electrons, some of them, they have been held bound there. So you have to heat. Heating is actually going to increase the size of everything around there, and that might free up the molecules as electrons. Good. So what are we saying here? So right, increasing the intensity Increasing the intensity. Causes an increase in the number of electrons ejected. Increasing the intensity of the light results in what?
An increase in the number of electrons ejected.
Good. Results in an increase in the number
Of electrons ejected.
of electrons
Ejected.
ejected. Very good. But and this is an examination kind of question. Because many people will think it is the frequency. So what does the frequency of the energy do? What does frequency do? It increases the kinetic energy of the electrons. Remember that frequency is the real definition of energy. I told you earlier. Whenever you see E equals to HF, F frequency is the form in which energy is stored. So when we say that, when you hear somebody singing and seeing buildings breaking, maybe glass breaking, and all those white people that used to sing on high pitch, you get it's because of what those pitch carries. It carry frequency. Pitch as a property of sound depends on frequency. And frequency causes vibration. You understand? You know what vibration can do. So the frequency of the sound wave, the frequency of the light and the incident light, the source incident
Frequency of
source incident light. Yes. Contributes or that is determines or serve as a determinant. Serves as a determinant. Serve as a determinant as to the as to the energy as to the energy of the electron ejected. This is the eh? You don't go come outside. I don't want to pin here. So I want to look at that Einstein's equation. Eh? Einstein equation of automatic effect. Uh, So yeah, no, it's not a new topic. It's still together. So you have the energy of the source to be equal to the work function of the overcome plus kinetic energy the electrons will gain. So the energy of the source is described as HF. Yes, this one HFO plus 1/2 mv squared. So one over two mv squared equals to HFS minus HF naught. So from there we can see mv squared equals to 2HFS minus HF naught. All right. So we have something we call stopping potential. While electrons, while the frequencies are busy trying to excite the electrons and move them off, you understand? We might also want to be in that situation where we can inhibit the release of electrons. At that point, we need what we call a stopping potential. So stopping potential it is the amount of work done to inhibit it is the amount of work done to inhibit the release of excited electrons. That is, energy will be greater than or equals to okay. Energy. Yeah. Hello. Okay. So I'm going to resolve the questions.
So, I saw a question on just from that topic.
Uh, Friends will not understand, they will just ask out. They explain.
So,
So,
first question.
I'm coming, sorry. Okay. A newly discovered star. A newly discovered star has its maximum radiation, at 240 nanometers.
Actually, I'm question number before.
At 214 nanometers.
Yeah.
Vitamin A, the surface temperature. B, the total power. The total power radiated per square meter if the star behaves as a black body.
That all?
Yes. Eh? No constants. Obviously, there might be some constants there. They're not right.
What's the question under where is displacement?
Huh?
What's the question under where is displacement?
Uh, modern physics. Modern physics.
How women are going to apply?
Let's go through the board.
Huh?
Go through the board. That's why I wrote everything well.
Okay.
Once you go through the board, you handle this. I don't know before. I don't know before.
Yeah.
I've done it before. Just there.
Yeah. Is the answer 12,075 Kelvin?
Hold on, let me- What do you call it?
12,075 Kelvin.
I didn't hear you.
12,075 Kelvin.
No, wrong, wrong. Wrong.
140 nanometers.
Uh,
This formula.
wait, sorry, it's true. Right. What's the second one? Over. What's the name again? Remind me, please. Ola. Uh, Ola. How are you? How's it going? The work. Well, you understand it now.
1 point. The power 1.2 times 10 to the power.
5 square.
Yeah?
Yes.
Okay.
And this is one.
Yeah.
Okay, yes, come on here.
Next question, sir.
A metal has a work function of 2.5 eV, 2.15 eV.
Yeah?
It is illuminated simultaneously.
Yeah.
A metal has work function 2.15 electron volts. It is illuminated simultaneously.
This
It is illuminated simultaneously
simultaneously.
by two monochromatic lights.
Okay.
By two monochromatic beam of wavelengths.
Okay.
Right. Metal, metal has work function 2.15 eV. It is illuminated simultaneously by two monochromatic beam of wavelength. 280 nanometers and 480 nanometer.
480 or 180?
480.
Okay. Sir,
Where do you stop?
480 nanometers.
Determine A. Which beam ejects photoelectrons?
Sir, I didn't get you.
Determine A. Which beam ejects photoelectron?
Sir, second part.
B. The maximum kinetic energy due to each beam. C. The stopping potential for each beam.
Is that all?
At E.
E.
Okay, part D. The threshold wavelength of the metal. Then part E. Explain why increasing the intensity of the 480 nanometer beam alone does or does not produce photoelectron.
Explain. Explain what, sir?
Explain why increasing the intensity of
Explain why increasing the
Explain why increasing the intensity of the 480 nanometer beam alone does or does not produce photoelectrons.
that it
Does or does not.
does not increase. Can you say the part E again?
Explain why. Explain why increasing the intensity
Of explain why increasing the intensity
of the 480 nanometer beam alone does not produce photoelectrons.
okay. Now,
No. No. Monochromatic. They are monochromatic beams. Eh?
yeah, what formula do we use to
That is nothing outside the ordinary.
tell?
It's nothing outside the ordinary.
What's outside the ordinary?
It's the same formula, it's just that we are going to use it. Yes. So what was the plan?
I'm getting it.
For that data, is it where we calculate the kinetic energy for both beam? That's the 280 and 480 nanometer. Then the one that have the value for the kinetic energy is the one that will be rejected. I mean, the one that will have a good electron.
I didn't get what I said.
And you have A. Is it where we calculate the kinetic energy for both the 280 and 480? Then the one that have a value for the kinetic energy, the one that eventually gets rejected. Or that gets the electron.
It's written in the question. Read your question.
Because you were giving one function and two wavelengths.
No, you still do.
I'm soon gonna rest. I'm soon gonna rest. 2 hours, 3 hours, I'm going to sleep. Eh? In 2 hours time, 3 hours, I'm gonna rest. Yeah.
So you just put one, just a work function and two wavelengths.
You're just expecting two work functions. So it's one surface now. Yes. Yes. When you solve it, what if the two of them have the value of kinetic energy?
When they have the maximum kinetic energy.
So because one wave has maximum kinetic energy. Hmm? Okay. What formula is
Using E equals B to find energy.
okay, so you have not found the energy since.
For finding the energy.
Yeah. Yeah.
So what is most energy?
You found that what?
Change this one is determining the average of your appearance. Change this one is determining the appearance of your appearance. That's so, in the absence of solution,
And it should be rejected because the energy emitted and the work must will give you the question.
thank you very much. So, what's the plan?
So about to calculate the maximum kinetic energy.
Okay. Yeah. No. How about you? Did you get the first one?
So
I'll do it now. I'll do it on the one.
the maximum energy is the maximum kinetic energy is 1 of 4.4 electron volts. That's 0.11 times 10 to the power minus 19 joules.
Now I speak grammar. You see, call that, those things you call them
The maximum kinetic energy is 4.4 GeV.
4x4.
Maximum kinetic energy is 2.45. That's 3.6 minus 90 degrees.
Okay. So that one is for which one?
So there are 18 nanometers.
So what happens in that one?
The more kinetic energy
Oh,
each GeV.
okay. So the other one now is not supposed to be there.
The other one is 0.2 times 10 to the power minus 20 joules or 0.45 GeV.
So what are you reporting now?
Potential.
That's so.
The stopping potential for the 280 nanometer is 2.25 eV, and for the 480 nanometer is 0.45 eV.
Okay. Okay. Yes. Okay. And the two eyes. So, we are done with that one now.
Only for the threshold wavelengths.
No, not far anymore.
For
Yes.
the threshold wavelength, we have 9.3 times 10 raised to power minus 7.
Mm.
Yes.
1 point.
9.3 times 10 raised to power minus 7 meters.
No, that one is wrong. Huh. You have to find the different thing to do. It's not correct.
So for getting that one, we're supposed to be using what function equals to reach to our lambda minimum. I think that's the threshold window.
It's now I know that.
Calculate the threshold wavelength. I'm supposed to be using what function equals to reach to over lambda minimum. That's the lambda minimum is threshold frequency, right?
Yes.
We did not use work function in EBO, we used it in Joule.
Yes, now you can't even use it in Navy. You can't use it in Navy. What the value that is divided? Generic. It's in your call. It's not me.
5.79 times 10 raised to power minus 7 meters.
For the threshold wavelength.
For the threshold wavelength,
This answer is what?
5.79 times 10 raised to power minus 7 meters.
Yes.
Okay.
Ah.
Now, for part E, we produce photoelectrons because the work function button there and the energy is different part of the source given in the question.
Well, I don't understand.
It will produce the 48 nanometer wavelength is going to produce photoelectron because the energy of the source is greater than the work function. And for us to have the electrons liberated from the surface, the energy of the source has to be greater than the work function. So we can have a kinetic energy to liberate.
People are talking like newscasters. Are you telling what you want to do or you're asking for it?
Well, why explaining that? Explain why increasing the intensity of the 480 nanometer beam alone does or doesn't produce photoelectron.
Oh, yeah, does it produce?
It does.
And you have answered it.
So, it's not explain.
You're not busy picking
I
them.
explain for you now.
Don't worry. Maybe you just meet them after this and explain to you. You did not do this topic before. Are you Jubel? Jubel. Jam. Jam. Okay, normal something. breathe. But
Next question.
uh,
Oh, yeah. Next question, sir.
so 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 okay, let's go. An artificial retina. An artificial retina contains millions of photoelectric cells with work function 2.05 EV. The retina receives monochromatic light.
Mm-hmm.
Uh,
The retina receives monochromatic light.
uh,
Uh-huh.
the retina receives monochromatic light of wavelength 520 nanometer. Determine photon energy. Determine photon energy. Determine photon energy, whether photon emission occurs, maximum kinetic energy, stopping potential, if the light intensity explains how visual signal changes. If the light intensity doubles, explain how the visual signal changes.
What?
Explain how the signal,
Explain how the
the visual signal changes.
I did not get
Alright.
light.
If the light intensity doubles, explain how the visual signal changes.
Okay. Signal.
Don't use myself. Who is yourself? Yes, this is myself. Huh? Do everything. I was wasting. Very sure I was wasting. What do you guys?
So for the photon energy,
Yes.
photon energy is 1.1 times 10 to the power minus 20 joules or 0.068 eV. Is that correct?
I'm from call it again. Call it again.
That the photon energy is 2.118 electron volts.
Photon energy.
Yes,
2 points.
118 electron volts.
Round.
That's 3.8 times 10 to the power minus 19 joules.
Yeah. Spirits.
Emission occurs. Emission will occur. Kinetic energy is Kinetic energy is 1.1 times 10 to the power minus 20 joules.
Again. Yes, let's go.
That's 1.1 times 10 to the power minus 20 joules.
No, no. No. Yes, no. Don't be maximum kinetic energy.
But the maximum energy goes to work on kinetic energy.
What do you do now? Sure. Alright. So I think for that maximum kinetic energy that people not get, you're using maximum kinetic energy equals to energy of the source minus. You will use maximum, that's your normal kinetic effect. Yes. So what's your work function? Then what's your energy of the source? 2 points.
So is the maximum kinetic energy 0.343 EV?
Yeah, yes.
So the stopping potential is 0.343 electron volts.
Stopping potential, yes. It has to be equal to the kinetic energy. So that one is valid. Okay, so
Yeah. So
yes.
if the light intensity, that energy of the source doubles, energy increases too. So therefore, the speed at which the light, the visual speed at which will be increased.
Repeat your statement.
If the light intensity doubles,
Yeah.
it leads to an increase in the kinetic energy also to be doubled too.
Uh,
So therefore, the speed at which the signal changes will be increased.
I see them. I see it. That can to read it. Right, is how we read it. You are talking fast, fast.
If the light intensity doubles, can you hear me now? The
Uh,
light intensity, the kinetic energy at which the signal is transferred will also be doubled. So
okay.
therefore, the eye will be receiving the information faster than usual, like twice than after
What is that then?
the eye, the way that the eye will be receiving the signal will also be doubled.
Okay. No. No. Even if I know you all those things before said at the beginning. You need to treat how you receive signal or
We
not.
achieve this visual signal changes to be decreased because the next energy becomes stuff.
Which person can I energy?
So this is the question. They said if the light intensity double, explain how the visual signal changes.
It cannot change. I don't want to know.
So
It
it
cannot
cannot
change.
change.
Your visual signal cannot change because it's a visual signal. It has been it is controlled by the prefrontal cortex. Maybe your own will change. No. James.
Next question, sir.
No. No. Enfin, I fit take my break like this. I fit take break like this now. Uh, so it works. A pot, the that one is very simple. Wait for me, please. Give me 30 seconds. Let me have an instruction for you. You will breathe. No, you will miss sleep. Okay, all right. Please let's be fast to answer this question. I don't have time.
Yes.
All right. A biomedical engineer. A biomedical engineer is developing a photoelectric blood oxygen sensor that detects light after it passes through a patient's blood. The sensor consists of a photocathode. With a wave sensor of the light passes through a patient's blood.
The sensor consists of a photo cathode with a work function of 2.30 EV. Yes. And is illuminated by monochromatic light. Of wavelength 480 nanometer. Of wavelength 490 nanometer. 480 nanometer. Vitamin. What is the vitamin? Vitamin A. The energy of an incident photon.
The energy of
An incident photon. B. Whether photoelectric emission occurs. The maximum kinetic energy of the emitted electrons. The stopping potential. Who said the bed? Who said the
E.
E. If blood absorbs 40% of the incident light. If blood absorbs 40% of the incident light. Explain how this affects the photocurrent. This affects the photocurrent and the accuracy of oxygen saturation measurement. And the accuracy of oxygen saturated measurement.
Sir.
Yeah?
That's all.
Yes. Yes, I will dress. I will dress. Finish, Steven. I don't know. Yeah. Alpha.
So,
Yeah.
for the energy of the initial proton, you have 4.15 times 10 raised to the power minus 19 joules or 2.6 electron volts.
I hate this topic.
Eh?
I hate this topic. This topic has proven that it cannot be other than the way it is. Something that, if you know the prompt I sent, I said prompts that I even use the word paralyze the person mentally.
That's correct.
I'm not saying anything. Read your question again for me.
The biomedical engineer is developing a photoelectric
I've seen it,
blood.
I've seen it. Oh, yeah. What's that first one? What's that first one?
I think you
What's the first one?
asked for the first one.
Yes.
You have 0.6 electron volt or 4.15 times 10 to the power minus 19 joules.
Correct. Perfect. Correct. Some people are just like that. Some people are just like that. Some people are just busy. Serious. There's no prompt to send.
For the maximum kinetic energy, you have 0.311 EV or 4.97 times 10 to the power minus 20 joules.
For what? Probably.
Yes, maximum.
Call the answer. No, man. No. Wrong.
4.97 times 10 to the power.
Still wrong, man. Sometimes you live to fight another day. Breathe again. Another day. It's not everything you will get now.
But still solving.
So
Almost a little bit. So if the blood absorbs 40% of the nutrient type, the in fact there will not even be kinetic energy cell because kinetic energy will be negative.
no.
So
So apparently
what is
the
it?
problem is that the photocurrents will decrease by 40%. When it decreases by 40%, the maximum kinetic energy and stopping potential will remain unchanged. We are talking about the human body here, senses. It's similar to what you did last one. They don't affect the rate of anything. They will decrease the photocurrent, all those parts, but characteristics, features remain unchanged. The worst case that the person will experience, mutations later.
So I think that the 40% effect has the 40% without has no effect on the
Yes.
current that happens. So it still continue working like that.
Yes.
Next question, sir.
No.
Why?
Treasure. Okay. All right. I think I'll just have to introduce you guys to some concepts.
Okay.
All right. So it's element of metaphysics, actions.
What's the next one?
That's what we do.
Okay.
So because we almost finished. So briefing through some of the very, very basic and important things.
I find it.
As I'm briefing through some of the things we're still going to be doing. Tomorrow, we run down to when we'll be finishing. So, topics like radioactivity and semiconductors, you don't want to miss them at all. Because we're going to be treating every single process of the treatment that is a semiconductor. Yes, and again, the worst thing we can do right now is to trivialize logic gates. In that semiconductors, because it can come out. Logic gates, yes, it can come out making use of the commands, and command or command. You actually have to do it. What is it? Can you hear me? You won't hear this. So you will have to treat those commands tomorrow. Yes. Constitute tomorrow. Gates with right logic arrangement, algorithm setups, and since we taught them for then the applied physics. And I said one of those that applied physics. I was sending that one to be after this event. I was sending a memo as to what they need to have in mind, those that are interested. So I treated it. I treated it in the program. It's strict. There's no aspect I didn't touch. I totally touched everything. Just as some days people, and I was expecting that those people that went around the probably live stream. That was in this live stream. Although everything is going to be uploaded on the YouTube channel. I will upload it.
Okay, sir.
The whole of it, so you can go and pick that side and watch it. He said, don't what? Now what?
This event, I mean, we get applied physics.
Yes. Fluid dynamics and fluid dynamics.
This event should
Yes.
applied physics.
Yes. Ah. So you think that will you go and take anything in the banner when you know that you are alive, that you are on life? You go and take a Juliana and I just take it.
6.
Okay, no, now. It has not reached. We're going to do it in the event. It was. No, I thought you were saying that Juliana is. I'm just I'm like, we have done it. Mm-hmm. So, also, we're going to touch everything. I believe we're going to touch it. So, that's so in our radioactivity, there's some extra calculation that we're going to be including. There's some extras that are going to be included. That's basically because of that's to also be to the benefit of the person. But regardless, I'm going to be treating nuclear physics, not radioactivity. You know there's a difference. The difference between nuclear physics and radioactivity. Radioactivity is just one side of the nuclear physics.
What do that ask under nuclear physics?
What?
What do that ask under nuclear physics?
There are many protonic physics called. Nuclear physics, you are only focusing on the nucleus in general. Nuclear physics studies, there is some part that is for neutron. There's some part that's for neutrons. There's some part that focuses only on proton. Some part focuses only on some that is broad.
Is that A-level syllabus?
It's not A level, it's like year 2. But we'll do it. That's what I'm saying. We'll try to do it.
Are we still having questions?
Now, I'm about to start touching randomly some topic because you guys have people are the ones that have to be busy doing the event. Things around. So I feel for you.
I'm listening.
You've been listening, you've been following up. The ones I said already in the past is not the issue. You can follow it up after the event. So, do you guys have any question that you have plan on asking me as regards any of these topics or even topics ahead of it?
So those electric, like when you have multiple fields,
Okay.
you just try how to resolve it and like get the result and that's because I for that particular child.
Yes, but there are two aspect of that, right? The one where what they are giving to you are forces. The one where what they are giving to you are field. So that one where they are field, sometimes the place they are going to do your resolution, no charge will be there. You understand what I'm saying, Abby? So no charge will be there. Maybe something like this now. So it's very possible that a charge is here, another charge is here, another charge is here, but there's no charge here. And it's field they want to get. They will ask you to calculate the field at this point. You have to check the field effect of this one here. So if this is a positive charge, you know field like to come out from positive charges. So nobody needs to tell you that from here it will be like this or anything like this. If this is a negative charge, you know that it will be like this. Because negative charges want field to enter here. So it will be trying to pull out field from this point. So all those kind of things. That's what we do. Yes. So once they are complete, you'll be seeing patterns that you can just resolve easily. Normal vector resolution, you see that it's something. The most difficult part of it is to get. The most difficult part of it is to get the free body diagram. You know to see here and okay, something's there, something's there, and just once you have gotten that one, that's finished.
So, under this binary equation, when you have two wavelengths, you're going to find like you have a first wavelength and you're giving only value of n1, you're not going to find out. And the second wavelength, you have n1. How do you find the second n?
I mean, you to get the wavelength. You can get the energy difference, then from there get the wavelength.
Okay.
You don't need to get it direct from relay.
What if you're giving only one energy difference? Is it possible?
One what?
One of the energy.
Okay.
How do you get it if you're giving two wavelengths?
No, the radiations can come out from one orbital motion now. Because you need to transit. You need to transit before you can start releasing radiation. If there's no transit, if it remains in that same orbit, it can't release any radiation.
So, in normal X-ray, what is the difference between both of them?
Your typical energy
Yes, and
is their form of, is their mode of operation.
okay.
That's their mode of preparation. Your typical energy is preparation is solidly just about thermionic emission. Just about thermionic emission.
Okay.
That one is just about thermionic emission. The radiations get released after you apply you, then you target to make sure that those radiations released are targeted to your target elements.
Okay.
And in the subatomic level, you know what's going on there. In the subatomic level, you know that okay, if it's a normal X-ray, it goes straight, knocks off an electron, another electron comes and falls in to cover up, and then you know that one is falling down to cover up. That will cause release of radiation. that radiation that is released, those electrons that fell just fell to cover the void because the targeted stream of radiation that was released that was fired at the target materials at the anode. I get what I'm saying. Hello.
Yeah, I can hear you. So I can hear you.
So the then when it fires, when it does fire, it's going to knock them off, and by knocking them off, it's going to it's going to cause it to refill the empty void.
Okay. How much about undervaluing catastrophe?
Now, ultraviolet catastrophe, all those has to do with violet color initially is the highest in the energy spectrum. And being the highest in the energy spectrum, Max, being the highest in the energy spectrum, they felt that they could see all brand of energy. But when it got to that, is that's it. This is it. Review and stuff. You get so that's it. They took video of it before starting. I saw when they took the video. But if people have asked me, I would have told you that you should have lagged one screen already. That's the best thing to have done. One screen should have been lagged already. So that it will show one continuous when it stopped, the one was running. Instead of letting it to stop. But that video evidence now they can consider it editing. illuminated with light of wavelength 300 nanometer.
Basis of the question, right?
Yeah. So determine the energy of an incident photon. Determine the energy of an incident photon. Then whether photoelectric emission occurs, the maximum kinetic energy. Let's just get the energy of the incident photon. What's the The metal has a work function of 2.20 eV and it's illuminated with light of wavelength 300 nanometer. Determine. Yes.
And a wavelength of
300.
300 nanometer. So as to find the energy of the incident ray
Yes.
and the maximum kinetic energy.
Just the energy of the cell.
The energy of the incident photon is 6.64 times 10 to the power minus 19 joules.
Okay.
Next
Yeah.
question.
Coming. So, run through the drag force F. The drag force F acting on a smooth sphere moving through a fluid depends on the drag force F acting on a smooth sphere moving through a fluid depends on sphere diameter G, fluid density rho, fluid viscosity mu, and flow velocity V. A. Obtain the number of dimensionless groups. The zero set is a variable.
Mu.
Yeah, viscosity, and flow velocity V. Using Buckingham pi theorem, determine A, the number of dimensionless pi groups. The number of dimensionless pi groups. A suitable set of repeating variable. The complete set of dimensional. Leave that at C, just NB.
Have you got it? Have you got it? No, I think that's reversed. Neden hazırladım? Bir harcayacağız. Okay. Universal answer.
The graph was actually smooth most actually smooth moving
It was F.
actually smooth moving through a fluid depends on the diameter E minus I.
Then I'm going to put this map on top of this guy. Show that this guy is independent of you. And having them your T minus 2. Surface sphere diameter D. Root depth 0. The dimension of this one is L. And the density viscosity. So that one now we have this M L1 T minus 1. Then we have the velocity. So we'll just pick one pattern. Sorry. How many variables do we have? 5.
5 variables, so our n is equal to 5. How many how many fundamental dimensions? 3. And everything is m and t. So m is equals to 3. So pi is equals to m minus 3, which is equals to 2. So we have two dimensionless pi terms. So what are they? For the pi one equals to, I'll pick my repeating variables. I can pick real VD. Anyone? Let's pick real VD. X, Y, Z. The dimension of this one is 1.
T1.
That's 3. Pi is the dimensionless something. Then you can pick any one of your choice of. Just make sure that the depending variable is not part. That the depending variable is not part of the one you picked. So in the first pi term, or in the second pi term, that's where you use it. Outside, not raised to the power of anything. I use 3 because there are 3 dimensions of fundamentals in here. Yes, yes. And I pick 4